Hi everyone, welcome to goclasses. In this lecture, we will continue our discussion of lexical analysis. In this lecture, we will study lexical analyzer implementation. In the previous lecture, in the part 1, we have already seen what is lexical analysis, what is lexical analyzer, what it will do. That we have already seen in the previous lecture, but in this lecture, we will study how it will do. Okay, how the lexical analyzer will work, how it will do the tokenization. So that is what we will study in this lecture. So you can see the lecture is lexical analyzer implementation. In the previous lecture we have seen what is lexical analyzer, or I can say what is this lexical analysis phase. In this lexical analysis phase, the source code will be converted to token stream. Source code, our source program, that is a character stream, and that character stream will be converted to token stream. So the lexical analyzer will convert our source code to a token stream of tokens. We have already seen what is a token, what is lexeme. Okay, all these concepts we have already seen in the previous lecture. You can see the first phase of the compilation process, that is lexical analysis. This is also called scanning. What the lexical analyzer will do, it will read your stream of characters, which is your source code. Your source code is a stream of characters. So the lexical analyzer will read your stream of characters, character by character, from left to right. So the lexical analyzer will read our source program character by character from left to right, and it will group the characters with meaningful sequences, okay, with some collective meaning, into lexemes. So let me tell you that what is a lexeme. Lexeme is basically in your source program a sequence of characters which has a collective meaning, I can say, which is a logical piece of source code, okay, which is a logical entity in your source code, that is called lexeme. Okay, so lexeme is the logical piece of source code, logical entity in your source code, that is called lexeme. And for every lexeme we generate a token, and you can see the token format. This is the token format. In the token we have two part, one is token name, another is attribute value. So you can see this attribute value, remember this is optional. For example, if you have identifier, means user defined name, user defined variable name, user defined function name. So if you have some identifier, then for that identifier, this attribute value, it can be either the lexeme as it is, or it can be the pointer to the symbol table location. In the symbol table where the information about that identifier is stored, okay, the pointer to that location we can store here. And remember, this attribute value, this is optional. For example, if you have a C keyword in your source language, if you have some keyword, then for that keyword, this attribute value can be missing. Okay, there is no need to put attribute value. You can only put the token name. So you can see this is the format of token. Remember, token is generated for every lexeme. What is lexeme? This is the part of original source program. This is this is the logical piece of source code which has a collective meaning, I can say, which is a logical entity in your source code, that is lexeme. And for every lexeme we generate a token. This is the token format. Attribute value is optional, and this token name, this is mandatory. Okay, very simple. So all these concepts we have already seen in the previous lecture. In this lecture we will study how the lexical analyzer will work. What the lexical analyzer will do, that we have already seen in the previous lecture, but how it will do, that we will study in this lecture. Let me tell you, in this lecture we will do a lot of practice. So first we will see the concept. For a short duration we will study the concept, but after that a lot of questions from the standard universities and also the gate pyqs I am going to solve. Okay, so this is going to be a very interesting lecture. Take your copy pen, a lot of practice we are going to do in this lecture. Okay, so let's start. How does lexical analyzer will work? So you can see what is lexical analyzer. Lexical analysis, this is a process which will convert our character stream into a stream of tokens. We already know this. And remember regular expressions from the theory of computation subject. In theory of computation subject, in the automata theory subject, we study regular expression. These regular expressions are going to be very helpful here. Remember what is a regular expression? This is a way to specify set of strings. So regular expression, this is a way to specify languages, regular languages, not all languages, but regular languages. So I can say regular expression, this is a way, this is a notation to specify set of strings. Okay, in the theory of computation, we study what is regular expression, how we write regular expression, what is the meaning of regular expression. So you can see regular expression, that is basically a way, a notation to specify set of strings, and this set of strings, this will be basically a regular language. Okay, so to specify, to describe the regular language, we can write a regular expression. Okay, now let me tell you that we can use these regular expressions to describe tokens also. Okay, so in our lexical analyzer chapter, why we use this regular expression? So you can see regular expression, we can use the regular expressions, we can use them to describe tokens. Okay, so remember we are discussing how the lexical analyzer will work, means how it will identify the tokens, how it will identify the lexemes, and for every lexeme we will write a token. Okay, so how to identify these lexemes and how to identify the tokens? So remember, for that we use regular expressions. So we use regular expression to describe tokens, or I can say we use regular expressions to describe the lexeme patterns, and for every lexeme we write a token. So you can read this specification of tokens, how to specify tokens, regular expressions. These are the important notation for specifying lexeme patterns. You already know for every lexeme we write a token. Okay, so remember what we do basically, some lexeme pattern is there. Let's assume this is a pattern. Okay, this is a lexeme pattern. This is a pattern for lexeme, for a particular type of lexeme. Okay, so you can see this is the lexeme pattern. For this lexeme pattern, what we will do, we will write regular expression. Okay, means this lexeme pattern we will describe using regular expression. This lexeme pattern we will describe using the regular expression. We will write a regular expression, and corresponding to that regular expression we will generate a token. Okay, so you can see corresponding to that regular expression we will generate a token. Okay, so this is the overall idea. I hope you understood. Means in your source program, remember the first task, that is to identify the lexeme. Once you identify a lexeme, then for that lexeme you can write the corresponding token. You can generate the corresponding token. Now, how to identify these lexemes? So for the lexemes, first you identify the pattern. What the lexeme pattern? For that pattern, you write the regular expression. You describe this lexeme pattern using the regular expression, and corresponding to this regular expression, we will generate a token. So this is the overall point. So regular expressions, these are used for specifying lexeme patterns. With example, this will become very clear. So let's take one example. Suppose we want to describe the set of all valid C identifiers. Means in the C language, we want to describe all the valid identifiers. Remember what is identifier? In the previous lecture also we have seen identifier. This is basically a token given to the user defined names. For example, user defined function names, user defined variable names. Okay, so you can see this identifier, this is a token given to the user defined names. Okay, now what we want to do, we want to describe the set of all valid identifiers in the C language. So basically we want to describe the lexeme pattern corresponding to the token identifier. Okay, this lexeme pattern, this we want to describe, for which we will generate the token, that is identifier. Okay, means we want to describe the user defined variable names, user defined function names. So the user defined names we want to describe. Okay, so how do we describe the lexical rule or the lexical pattern corresponding to the identifier token? How can we describe identifier? Tell me, how can we describe identifier in the C language? We want to describe identifier when we are giving the name to a variable or to a function. So the user defined name we want to identify, we want to describe it. Okay, so how to describe it? Now let me tell you, in the C language, what is a identifier? Let me tell you, or I can say what is a user defined variable name. Let me tell you. So identifier is basically a sequence of letters and digits. The first character must be a letter, and remember the underscore, that will be counted as a letter. and uppercase and lowercase letters, they are different. That's it. This is the definition. This is the description of identifier token. This is the description of pattern for which identifier token will be generated. Once you have this description, then this description we will call it identifier lexeme basically, and we will generate the token that is identifier. Okay, so remember, in the C language, what is identifier, or I can say what is a user defined name. So you can see identifier is a sequence of letters and digits only. You can either use letters or you can use digits, but the first character must be a letter. Underscore you can use, no other special symbol you can use. Remember, underscore will be counted as a letter, means you can start with underscore because the first character must be a letter, and underscore is treated as a letter, and uppercase lowercase letters are different. That's it. So this is the English description of identifiers in C. This English description, remember, we can convert into a regular expression also. But before that, let's take some examples of identifiers. In the C language, let's take some examples of user defined variable names. So can you tell me? You can see the first letter must be a must the first character must be a letter. Okay, so you can see, for example, I can start with this ABC. Yes, this I can give. This is correct. Okay, can I start with 9? This digit, can I start with like for example 9AB? No, this I cannot do. Okay, remember, I can start, the first character must be a letter. Okay, for example L, and then after that any sequence of letters or digits, and underscore will be treated as a letter. So you can see after this L you can write, for example 9 you can write. Okay, you can write A, you can write B, you can write underscore, you can write whatever you want, 0. Okay, and here capital M you can write. Okay, so like this. So this is also identifier. Okay, you can start with underscore, no problem, underscore. Now this is the first character. Now after that any sequence of letters or digits. Okay, so for example 9 AB, this is also perfectly fine. For example 9, no, this is not a user defined variable name, this is not identifier. Okay, for example A, that is perfectly fine. I, that is perfectly fine. Okay, in the C programming, when we write a program, then many times we use this variable name, right? Yes or no. For example J, we use this variable name. Okay, K, we use this variable name. So all these are allowed. Okay, and for example underscore AB, this is also perfectly fine. Underscore 89, this is also perfectly fine. Okay, so I hope you understood the point. But remember, you cannot start with a digit. Okay, for example you cannot start with 8, then 89 AB. Okay, this is not allowed. Okay, and remember, you cannot use any other symbol. For example, can you use this at the rate symbol, at the rate AB? No, this you cannot use. Okay, is this clear? We cannot use this. For example, can I write like this, AB then dollar? Okay, then 9. No, this also we cannot write. So I hope you understood the point. Now let's see the regular expression that will describe identifier. The English description we have already seen. What is identifier in the C language? Identifier in the C language, that is a sequence of letters and digits. The first character must be a letter. Underscore is a letter. Uppercase, lowercase letters are different. Now let's assume this letter underscore. Let's assume this is set of all letters and underscore. So remember, we are describing a set, that is letter underscore. What is this? This is a set. And in this set, what we have? We have all the letters and underscore. Remember, uppercase, lowercase letters are different. So remember, here we have, for example, A, B, capital Z. Okay, capital A to capital Z, small a, small b to small z. Okay, next, also underscore, also underscore. Okay, this underscore, this is also treated as letter. And what is digit? This is the set of all digits. Okay, 0 to 9, 0, 1, 2, and so on 9. This is the digit. Okay, so how to write the regular expression for to describe the identifier? Tell me. Very simple. The first character must be a letter or a underscore, because underscore is also a letter. Okay, we treat underscore as a letter. So remember, the first character must be from this set. Okay, The first character must be from this set. But after that, any letter or underscore or digit, okay, any number of times, any sequence of digits or letters you can have. Only this is the condition that the first character must be a letter or an underscore. So this should be the first character. After that, any sequence of letters or digits is fine. This star means what? Let me tell you, this star means zero or more times, zero or more occurrences of. This is what it means. Okay. What this plus means? This means union, or I can say or. This means or. Very simple. I hope you understood this. This we study in the regular expression topic in the theory of computation subject in the automata theory. You can study from there what is regular expression. Okay. That is a prerequisite basically. When we study compiler design, then the prerequisite is finite automata, DFA, NFA, regular expression. And when we study syntax analysis, then the prerequisite will be CFG grammar basically. Okay. So context free grammar. So these are the prerequisites. Okay. Nothing else is a prerequisite. Okay. Only these are the prerequisite before you study compiler design. Okay. And these concepts we study in the theory of computation automata theory subject. Okay. So overall, this is the idea. We could describe the C identifier by this regular expression. So this is the regular expression that we got. You can see the first character must be a letter. Underscore is also a letter. So you can see the first character must be from this set, letter underscore. Okay. The first character must be from this set. After that, any sequence of letters or digits. So you can see either letter or underscore or digit star. Star means zero or more times. So basically any sequence of letters or digits. So this is the regular expression that will describe the C identifiers. Okay. This will describe set of all C identifiers. Very simple. And remember, corresponding to this regular expression, we will generate a token that is identifier token. Okay. Very simple. I hope you understood. So we have seen how to specify tokens. So we will use regular expression to specify lexeme patterns. For every lexeme pattern, we will write a regular expression. Corresponding to that regular expression, we will generate a token. So you can see we use regular expressions to describe tokens. Or I can say we use regular expressions to describe the pattern corresponding to tokens, to describe the lexeme patterns corresponding to tokens. Very simple. Let's see this example. With this example, everything will become very clear. If there is any confusion with this example, it will become very clear how the lexical analyzer will work. Okay. So read this question. You can see, consider the following flex like specification. Right now, don't focus on this flex. Okay. I will tell you in this lecture, I will tell you what is this flex. But basically, consider this specification. The alphabet is set ABC. Very simple alphabet. Only three symbols are there, ABC. Parenthesis is used to show the association of operations, and parenthesis is not part of input alphabet. In the input alphabet, you don't have parenthesis. Only these are the three symbols in the input alphabet ABC. You can notice that for this pattern, or I can say for this regular expression, corresponding to this regular expression, we will generate token 1. I told you that for every regular expression, corresponding to every regular expression, we will generate a token. Yes or no? Okay, remember, first you find the pattern, lexeme pattern. For the lexeme pattern, you write regular expression, and corresponding to a regular expression, we will generate a token. So here you can easily see that this is a regular expression, and corresponding to this regular expression, we will generate token. We will return the token 1. Corresponding to this regular expression, we will return the token 2. Okay, very simple. Now you can see, show how the following string, this is a string given to us. This is the input character stream. So show how the following string would be partitioned into tokens. Because right now this is a character stream of characters. Now we need to find how the tokenization will happen, how it will be converted to stream of tokens. So you can see, show how the following string would be partitioned into tokens by grouping the characters into lexemes. First, you group the characters into lexemes, and for every lexeme, a token will be generated. Label each lexeme with the integer of the correct token class. You can see these are the token classes, token 1, token 2. Next, you can see blank in the string. These are put just for readability. Here all the blanks that are there, these are just for readability. These are not part of the string. Okay, in the string you don't have any blanks. These are just for readability. Without blanks, if I write, then it will not be readable. Okay, so just for readability we have put blanks here, but these are not part of string, or you can assume that there is no blank here. Okay, now let's see for this character stream how the tokenization will happen. So you can see, remember, this is our input character stream, and this is the input to the lexical analyzer. And what the lexical analyzer will do, this character stream will be converted to token stream. Now let's see how it will happen. Here you can see we have taken a very simple lexical analyzer. We only have two tokens in our lexical analyzer. Okay, let's assume we are designing a lexical analyzer, and it is a very simple lexical analyzer. So you can see we only have two tokens. Okay, and these two tokens, they correspond to these regular expressions. Okay, now you can see what the lexical analyzer will do. It will read the character stream from left to right, character by character, yes or no. Now you can see, first we will read this character. Okay, now tell me, among these two regular expressions, which is a perfect candidate, which is a candidate right now in the race. Okay, let's assume basically these two regular expressions, these are the candidates. Now among them, who is the candidate now? When you read this character C, so you can see this regular expression is not a candidate, because this regular expression means we must have AAC. Okay, this will start with A, then again A, then again C. Okay, so you can see, yes, this is perfectly fine. Remember what this means, BA or C. Okay, please understand this plus means or. So actually this basically means BA or C. Okay, this is what it means. And what this regular expression means, let me tell you, this means AAC. Okay, very simple. So you can see the lexical analyzer will read the character stream from left to right, character by character. Right now you are here. Now when you are here, then definitely this regular expression is not a candidate. This regular expression is a candidate. And in this regular expression also, there are only two strings, BA comma C. So yes, C is matching. So that's it. Okay, so we got our lexeme. Is this clear? We got our lexeme. And tell me, for this lexeme, which token will be generated? Corresponding to this lexeme, which token will be generated? That is token 2. Okay, yes or no? So token 2 will be returned here. That's it. Now again we will start here. From here we will start. Who is in the race? Who is the candidate? These are not the candidate, because here you can see this is BA, this is C. Okay, so definitely AAC. This is the candidate. So you can see we got AAC. Yes. Okay, AAC we got. So remember, that's it. We got our next lexeme. So we got this lexeme. And for this lexeme also, a token will be generated. You can see corresponding to this lexeme AAC, corresponding to this regular expression, the token generated is token 1. Token 1 will be generated. Okay, very simple. Next, now we will start from here. B, who is in the race? Only this regular expression is in the race. Okay, so you can see BA. Yes, we got BA. Okay, perfect, no problem. So here I can say that we got our next lexeme. For this lexeme also, this is our lexeme. And corresponding to this lexeme, which token will be generated? Token 2 will be generated. Okay, now you can see then C, who is in the race? Only this regular expression is in the race. Okay, that C is there, that's it. Okay, so you can see here also token 2 will be generated. Okay, token 2. Here also token 2 will be generated. Yes or no? Like this. Then you can see now we got AAC. Okay, AAC. Yes or no? This AAC we got. For this token 1 will be generated. And after that you can see we got C. Okay, so I hope you understood this point, that now you can see token 2, for this token 2 will be generated, for this token 2 will be generated. Okay, so you tell me, the input character stream is this. What will be the output token stream? So let me know what will be the output. The output will be basically, you can see, first we are generating token 2. Okay, for convenience I am writing this token 2. Okay, let's write T2. Okay, for convenience, so that I don't have to write the full spelling. Okay, for convenience, let's assume this is token 1. So you can see the output of the lexical analyzer, what that is? That is token 2, T2, then T1. Okay, then you can see T2, T2, T2. Okay, then you can see T2, T2, T2. Okay, next after that, T1, T2, T2, T1, T2, T2. Okay, that's it. I hope you understood this point. Okay, so remember, this will be the token stream, this will be the output. I hope you understood. Very simple point, right? Now let's study what are the challenges in scanning in the lexical analysis when we generate tokens. What are the challenges in scanning? Let's see the challenge 1. That is, when there are multiple ways we could scan the input. When you are scanning the input character stream, when we are scanning, then when there are multiple ways we could scan the input, how do we know which way to pick? With example, it will become clear what is this challenge 1. So let's take example. Consider a very simple lexical analyzer which has only two tokens. So you can see these are the two tokens. We have token 4 and token identifier. There is a 4 token, there is an identifier token. You can see this 4 token is generated corresponding to the keyword 4. So you can see for this token, this is the lexical rule, or I can say this is the regular expression, or I can say this is the lexeme pattern. Means for this pattern, this token generated, and identifier token that is generated corresponding to identifier. You can see this is identifier, right? The first character must be a letter. So you can see underscore is treated as a letter. Okay, so the first character that is a letter or an underscore. Okay, and after that you can have any sequence of letters or digits or underscore. Okay, remember uppercase letters, lowercase letters, they are treated different. They are different basically. So overall, this is a very simple lexical analyzer with only two tokens, and corresponding to these two tokens, this is the lexical rule, or I can say regular expression, or I can say lexeme pattern. Now, this character stream we have, this is the input character stream. Let's see what will be the tokenization of this character stream. So remember, this is our input character stream. FORT, four characters. So this is input character stream. Okay. Now for this input character stream, how the tokenization will happen? Think about it. Now let me tell you. Maybe person one is thinking. Maybe person one is thinking that this fort, this complete, I can say, from we will start from here. The lexical analyzer will start and it will read the characters from left to right, character by character, one by one. Okay, you can see the person one, what the person one can say. The person one can say, sir, this entire fort, this is matching the identifier token, yes or no? Because you can see the first character is a letter, then any sequence of letters or digits or underscore. Okay, so here you can see that this complete fort, this is matching, this is a lexeme and this is matching the identifier token. Okay, yes or no? This is what person one can say. So person one can say that, sir, generate token identifier. Okay, for simplicity, again let me call it T1 and let me call it T2. Okay, this is just for simplicity so that I don't have to write these big names. Okay, so let me just call it, for my convenience, let me call it T1, and for my convenience, let me call T2. Okay, so you can see what the person one can say. Person one can say that, okay, sir, generate token T2, means token identifier, that's it. Okay, only one lexeme will be there, and this will be the generated token. This is what person one can say. Do you agree? What person two can say? Can you tell me? Person two can say that, sir, we are reading from left to right, character by character. See, sir, this four, this is matching the T1 token. Yes or no? This is matching the regular expression for token T1. Okay, so for this 4, let me generate token T1. Okay, now for this T, I will generate identifier token. Okay, means T1, T2, that's it. This is what person 2 is thinking. What person 3 will be thinking? Person 3 is thinking that, sir, we are reading from left to right, character by character. Now, when you read this first character, this itself is matching with the identifier token. Yes or no? This first character, this is matching the regular expression corresponding to identifier token. So for this F, generate token T2. Then for this O, generate token T2. For this R, generate token T2. For this T, generate token T2. Okay, yes, makes sense. Yes or no? Now, what the person 4 can say? Tell me. The person 4 can say that, sir, let's generate token T2 for FO, token T2 for RT, T2, T2. Okay. What person 5 can say? Tell me. What person 5 can say? Person 5 can say, sir, for this F, generate T2, then ORT, generate T2. Okay. So you can see actually T2, T2, but here you can notice this person 4 is saying that FO, according to person 4, FO is a lexeme, RT is a lexeme. According to person 5, F is a lexeme, ORT is a lexeme. Okay, yes or no? If you want to write the lexeme, then according to person 1, this entire FORT is a lexeme. According to person 2, this 4 is a lexeme, and then T is a lexeme. According to person 3, F is a lexeme, O is a lexeme, R is a lexeme, T is a lexeme. Okay, yes or no? I hope you understood the point. Many more possibilities are there. What are the many more possibilities? What person 6 can say? You have already understood the point that this is a challenge. Yes or no? This is the challenge in scanning. There are many more possibilities. For example, the person 6 can say that, okay, for F, generate token T2, OR, generate token T2, T, generate token T2. Yes or no? T2, T2, T2. Okay, basically, the lexemes according to person 6, these are F, then OR, then T. Okay. I'm not going to write all the possibilities, but many more possibilities are there. Okay. So you can see, and so on. Some more possibilities might be there if we did not cover. Okay. But overall, you understood the point that this is a challenge. Yes or no? So, what was the challenge? Remember, I told you the challenge was that when there are multiple ways we could scan the input, then how do we know which one to pick? You can see these are the multiple ways you can see on your screen. These are the multiple ways we can scan the input. In different ways we can scan the input. So which way to pick? That is a challenge. Agree? So what is the solution now? You can easily notice in this photo, in this screenshot, you can see that this was person 1, this was person 2. Do you agree? This was our person 1, person 2. Okay. Then you can see person. Next, you can see, for example, this is another person FORT. Okay, then this is another person FOR, comma T, and so on. Okay, this is another person FORT. This is another person FORT, all separate. Okay, so basically, these are different possibilities. Okay, so I hope you understood the challenge. Now, once you understood the challenge, now let's see the solution. What is the solution? You can see the challenge in scanning, the challenge one, that is when there are multiple ways we could scan the input, then how do we know which way to pick? And the solution is longest match. That's it. Very simple solution. The solution is longest match we will take. This is also called maximal Munch. You can call it longest match or you can call it maximal Munch. What this longest match solution says, let me tell you. It says that you keep going. Okay, basically you take longest possible match which matches some regular expression. Definitely it must match some regular expression, but you take longest possible match. Very simple. Okay, so let's read this. What is this longest match solution, or I can say maximal Munch solution? This is basically that we should find the longest match accepted by the lexer. Means we should find the longest match possible, which is accepted by some, which is matching some regular expression. Okay, so longest match we should find. Means what I can say means always match the longest possible prefix of the remaining text. Whatever longest possible match you can find, which is matching to some regular expression, that you find. Okay, I hope you understood. So this is a meme. There is a serial, Friends. Okay, this is from that serial. If you have watched it, the Friends TV show, if you have watched it, then you will relate to it. Basically, there is a scene in this Friends TV show where this Ross tells Rachel that you go long. Okay, so he doesn't let her play. So he just says you go long. Anyway, so you can see this is a meme. You can relate to it if you have watched the this TV show. So you can see this is the definition of longest match or maximal Munch. Okay, basically you go long, you find longest match possible. Okay, as long as longest match possible, which is matching some regular expression. It must match some regular expression. That longest match we will take. Okay, very simple. So in this example, what we are going to do, here we have two tokens, and these are the corresponding regular expressions. Or I can say for these two tokens, these are the corresponding patterns. So tell me, for this FORT, what will be the correct tokenization? We will read this character stream from left to right, character by character. Okay, you can see we will read this F who are in the race. Both the tokens are in the race. Yes or no? When we read this character, then this F is also this for token is also in the race, and identifier token is also in the race. Then we will read O. Both the tokens are in the race. Then we will read R. Both the tokens are in the race. Now, at this moment, remember this for token is matching. Okay, at this moment, this for token is matching. But we will go long. Yes or no? You go long. So let's go long. You can see so far the for token is matching. Okay, but you go long. Now you can see after reading this symbol, this identifier token is matching. Okay, so what we will do, we will take the longest possible match, which is matching some regular expression. So always take the longest possible match, which is matching some regular expression. So you can see here we will discard this. Okay, we will not generate a for token, we will not generate it. Basically we will generate the identifier token, and this entire thing will be the lexeme. Okay, so I hope you understood this point. So remember, for this character stream, what will be the output? The output will be T identifier. Only one token will be generated. And what will be the lexeme? Okay, this is the token generated. This is the token name, and the lexeme, that is FORT. This is the lexeme. Okay, so please understand, this is the token name, and this is the lexeme. That's it. I hope you understood the longest match. The solution, did you understand? Please tell me. So this is what we have seen, that when there are multiple ways to scan the input, this input we can scan in multiple ways. So when there are multiple ways to scan the input, then which way to choose? So that is the challenge. That is the challenge one. And for that challenge, the solution is longest match, or I can say maximal Munch. So you can see for this character stream, the output will be identifier token, and this entire fort, this will be the lexeme. Very simple. Let's see this example. This is an interesting example. In this, you will understand the maximal Munch or longest match. This is a perfect example to understand longest match. So let's see. We have three tokens now. And for these three tokens, this is the corresponding regular expressions. You can see there is a do token, there is a double token. These are the keywords. Assume you have C language. In the C language, these are the keywords. Okay, you can see for the do keyword, the token is do. For the double keyword, the token is double. And there is a mystery token. Understand one thing. This mystery token, remember, it is a single letter. There is no star here. Please understand. Is there any star here? This mystery token look at the regular expression corresponding to mystery token. Is this a sequence of letters? No, this is not a sequence of letters. This is a single letter. Okay, please understand. This is a single letter basically. Basically a single letter. Okay, means this is basically either A or B, capital Z, from capital A to capital Z, or from small a to small z. Okay, yes or no? So please understand that this mystery, this token, if you see the corresponding regular expression, you understand there is no star here. This is not a sequence of letters. This is a single letter. Okay, very simple. Now, this is the input character stream. You tell me how many tokens will be generated, how the tokenization will happen, what will be the lexemes, the sequence of tokens, the stream of tokens, the output you suggest. Okay, tell me. Pause the video, try this question. Very interesting question. Now, let me solve it. So you can see these are the three tokens and these are the corresponding regular expressions. We will read this character stream from left to right, character by character. Okay, so when you read this D, who is in the race? Tell me, who is in the race when you read this D? For a moment, assume that here this is capital DO and this is capital double. Okay, is this clear? I think because here you can see they are saying that capital and small letters, they are distinguishable. Okay, but actually these are the keywords, so I think it doesn't matter. Okay, because these are basically the keyword. Okay, in the identifier, this capital and small, this might be distinguishable, but in the keyword I don't think it matters. Okay, in the C language, what do you think? In the C language, if I write a keyword, for example int, or if I write int, these are considered same, right? Because this is basically the keyword. Yes or no? So from the keyword point of view, this uppercase, small case, this doesn't matter. But from the identifier point of view, from the user defined names point of view, this small and uppercase letters, uppercase, lowercase letters, these are different. Okay, so now let's see. Now when you read this D, then who is in the race? All of them, yes or no? Because this is a single letter. This is DO, this is DOUBLE. So when you read this character, then all of these three tokens are in the race. Okay, so what we do? We go long. Okay, so let's go long. So here you can see you will read this O. When you read this O, at this moment, a token is matching. Which token is matching? You can see this do token is matching. Yes or no? Do you agree? This do token is matching. But remember, we will not generate right now because we will go long. Okay, yes or no? This is just to track. Okay, I am just marking it that this is the last point so far where some token is matching. Okay, this is the last point so far. This is the marking that so far this is the last point where some token is matching. Okay, but we will go long because of maximal Munch. So you can see you will read this character U. Now tell me who is matching. This is entire thing. Please understand. Now remember, this mystery is not matching anymore because this mystery, this token mystery, this was a single letter. You started from here. This entire thing you are seeing DOU. Okay, please understand. Don't look only this character. We started from here. We started from here. So this DOU, is this matching? Now remember, this is matching this regular expression. This is not matching this regular expression, not matching this regular expression. So you can see right now we are in the race. This double token, this is in the race. Okay, but so far there is no match. Yes or no? It is in the race, but there is no match. Next you will read B. Still this is in the race, but right now there is no match. Okay, next D comes. That's it. Now this is out of the race. Do you agree with me? When you read this character, then you can see DOUBD. DOUBD. Now this token is out of the race. Okay, so what we will do? We will backtrack. We will go back. We will go back. What was the last point? What was the last matching regular expression? The last matching regular expression, that was this token do. Yes or no? Okay, so remember, we went so far. Okay, we were going, but you can see here you can stop, and now you go back and you find the last matching regular expression, last matching token. So that is basically do token. Okay, so that's it. So we got our first token, that is do. Okay, is this clear? So this do token will be generated. Okay, this will go in the output. Let me write the output. The output will have this do token. Okay, this will be there in the output. And what will be the corresponding lexeme? The corresponding lexeme will be do. Okay, now remember where we will start. Now we will go back and we will start from here, because so far we have done the tokenization. Okay, this we have already done. Now again we will start from here. So we will read this u first. Tell me, when you read this u, now we are starting from here. The remaining string we need to read. Okay, this remaining string. So tell me, when you read this u, which token, which regular expression is in the race? This is not in the race. This is not in the race because they will start from D. Basically, yes or no? So when you read this U, only this, only this regular expression, this mystery token is in the race. Okay, but you can see this mystery token. This is a single letter. Okay, this corresponds to a single letter. So I can say that here I can stop, and here I can say that this mystery token will be generated. Okay, is this clear? This mystery token generated. Now where we will start? We will start from here. Basically, the remaining string we need to read. Now, when I read this B, which regular expression is in the race? These are not in the race. Only this regular expression, the mystery token, is in the race. So for this B also, but because remember the mystery token regular expression you see, that is basically a single letter. Okay, so you can see for this B also a mystery token will be generated. T mystery. Okay, is this clear? So you can see the output that you are getting. Let me write parallelly the output that you are getting. First token is do token, then mystery token, then again mystery token. Okay, after that you can see, now we will continue reading from here. The remaining string we need to read. So far we have done the tokenization, so the remaining string we need to read. Okay, in the remaining string, when you read this character, you are standing here, remember. When you read this character, which regular expression is in the race? Right now, all of them. Right now, all of them are in the race. Now, you will go long. Yes or no? So just go long. So when you read this O, now who is in the race? Just tell me. Now who is in the race? You can see now this mystery token is out of the race. This regular expression is not in the race, out of the race. Only these two regular expressions are in the race. Yes or no? Okay, but what we will do? We cannot stop here because we will go long. But remember one thing, so far, you can notice so far, this regular expression, or I can say this token is actually matching. So just mark it. Just put a marker here. Please put a marker here that, okay, that do token was actually matching here. Okay, this marker you can put that do token is actually matching so far. So far, you can see this do token is matching, but we will go long. Okay, so you can see you will read this character DOU. Now who is in the race? Now this is not in the race, this is not in the race, only this double token is in the race. Then you will read this B, still this double token is in the race. Then you will read this L, still the double token is in the race. Then you will read this E. Now the double token is also completed, or I can say now the double token is also matching. So you can see you can remove this last point. Yes or no? Now you can remove this last point. Now you can remove it. Let's remove it. Okay, now you can see here this double token, or I can say this regular expression is matching. So because of longest match, this token will be generated. This D double, this token will be generated. Okay, so that's it. D double. I hope you understood this point. So total, how many tokens will be generated? 4 tokens will be generated, and corresponding lexemes also I'm writing. You can see these are the corresponding lexemes. I hope you understood this example. This was a beautiful example, right? Because here in this example, notice one thing, you also need to backtrack, because when you were starting from here, initially you are here, when you are starting from here, you can see when you read this character so far, all these three tokens, all these three regular expressions are in the race right now. But when you read this next letter, next character, then you can see now this regular expression is not in the race. Okay, one more thing, you can see when you read this D, here remember this mystery token, or I can say this regular expression is matching. So you put a pointer here, please understand. You put a marker, that okay, this mystery token is matching. Yes or no? Because you can see here mystery token is matching. But here remember, when you read this D, then these two tokens, these two regular expressions are in the race, but they are not matching. They are in the race, but they are not matching. Do you agree with me? Okay, when you start reading this character stream from left to right, character by character, when you read this character D, then at this moment you can see these two regular expressions are in the race, but they are not completely matching. Yes or no? But you can see this mystery, or I can say this regular expression is fully matching. So I can put a marker here that okay, this is matching. Okay, if nothing else will match, then I will generate this mystery token if nothing else will match. But I will go long. Okay, so here you can see I will read this O. Now at this moment, this do token is matching, or I can say this regular expression is now matching, fully matching. Yes or no? This double is in the race, but this is matching. So I can remove this previous marker, because now I got a new marker. That new marker is TDO. This new marker I got. Okay, but still I cannot stop. Okay, because of longest match. So keep going, you will read this U. Now you can see this double is, this regular expression is in the race. You will read this B, DOUB. Focus on this DOUB. This is in the race. Now you will read this D, DOUBD. Now this is out of the race. So now you will go back, you will do the backtrack, you will go back, and you will find the last matching regular expression. Okay, this is the last matching regular expression. Yes or no? So for this last matching regular expression, for this you can see token will be generated. Okay, so you can say that okay, that's it. This will be your lexeme, and this is the token that will be generated. So you can see the output. You can see that will be TDO corresponding to the lexeme DO. Okay, I hope you understood the point. Is this clear? Of course, the complete explanation also we have seen here, the complete explanation. But this initial part I just wanted to explain, because this is very important. Okay, so always put a marker. What is the last matching regular expression? Okay, is this clear? Keep track of last matching regular expression. Keep track of it. Keep track of it. Put a marker. So that in the future, if nothing else will match, if no longer match is there, then we will generate a token for this. I hope you understood this point. Okay, so put a marker, keep track of the last matching regular expression. So in the future, if there is no longer match, because we are going for the longest match, but in the future, if there is no longer match, then we will generate token corresponding to this last matching regular expression. I hope you understood this complete explanation. Very interesting example we have taken. So you can see for this input character stream, the output will be this. Okay, this is the lexeme. You can see this is the lexeme sequence. Very simple. Now let's see how to implement maximal munch. Let me tell you, you can implement maximal munch by creating NFAs also. But actually, to solve the questions, we will not do this. We will not create NFA when you are solving the questions. So let me tell you, theoretically, I can say conceptually, when you design the lexical analyzer, then basically what you will do, How you will implement the maximal months? So basically, for all the regular expressions, you will generate NFA, and then you will run the NFAs in parallelly. Okay, I will tell you with example, I will explain. But the points, let me tell you, in the GATE exam or all the questions that we will see in this lecture, in those questions, we are not going to generate NFA, DFA, these things. We are going to directly solve the question from the regular expressions. The same way we have done the previous questions, the previous 2 3 questions that we have done, the similar way we will solve all the questions. But conceptually I can say how to implement the longest match. Let's see that. Okay, so you can see implementing longest match or maximal months given a set of regular expressions, because you have a set of tokens, and for those tokens there are corresponding regular expressions. So given a set of regular expressions, how can we use them to implement maximal months or longest match? So this is the idea. Convert all the regular expressions to NFAs, non-deterministic finite automata. This concept we study in the theory of computation, automata theory subject. So you can see, convert all the regular expressions to NFAs, run all the NFAs in parallel, keep track of the last match. This I already told you. Yes or no? Keep track of the last match. Okay, then you can see when all the automata get stuck, then you report the last match, means you return the last match. You generate a token corresponding to the last matching regular expression. Okay, then you restart the search from that point. Okay, means if you have done so far, if you have done the tokenization so far, then you will restart your search from this point onward. Okay, so this is the idea. I hope you understood this point. Now with example this will become very clear. So let's take the same example, these 3 tokens, and these are the corresponding regular expressions. So what we will do, I told you, to implement the maximal months, these regular expressions we will convert into NFAs. How to create the NFA for these regular expressions? You can see this is the regular expression DO. How to create the NFA? Very simple. The first character must be D, then the next character must be O, then final state, then nothing else should come. Yes or no? The first character must be D, the next character O, then you go to final state, that's it. But nothing else should come. Okay, in this final state nothing else should come. What about this double? You can see the first character must be D, the next character must be O, the next character must be U, the next character must be B, the next character must be L, the next character must be E, and then you go to final state. But remember, in the final state nothing should come, no more characters should come, nothing should come, nothing more should come. Okay, what about this? This is just a single character. Yes or no? This regular expression means a single character. So from the initial state you can see one letter should come. This is a single letter. Okay, so remember, one letter should come, either capital A, capital B, and so on, capital Z, or small a, small b, and so on, small z. Basically only one letter should come, that's it. Then you go to final state, nothing more should come, no more extra letters should come in the final state. So this is how you can convert these regular expressions to NFAs. Okay, so finally these NFAs you will get. Now this is the input character stream. What we are going to do, basically the same concept we are going to apply. Okay, we will read this character stream left to right, character by character. When you read this D, then you run all these DFAs in parallel. Okay, so tell me, we are running all these NFAs. When you read this D, run all these NFAs in parallel. Okay, so tell me one thing. When I read this D, I am running all these NFAs in parallel. Where I will be in the first NFA. In the first NFA, I will be here. In the second NFA, I will be here. In the third NFA, I will be here. So in the third NFA, I am in the final state. Agree or not? When I read this character D, I am running all these NFAs in parallel. So you can see from the start state, we will start. When you read this symbol, when you read this character D, then in the first NFA, I will be in this state. This is not a final state. In this NFA, I will be in this state. This is not a final state. So basically, we are in the race. Yes or no? We are in the race. But here you can notice in the third NFA, we have gone to the final state. So means you can mark it here. Okay, you can mark that this is the last. So far this is the last matching regular expression. Okay, so I can put a marker here that okay, so far this is the last matching regular expression because you are in the final state. Okay, but remember, because of longest match, we will not generate this token immediately. We will wait. Okay, yes or no, we will read the next character. When you read the next character, keep running all these NFAs in parallel. Okay, now you can see after this D, when you read this character O, then this first NFA will be in the final state. The second NFA is in the race but not in the final state. And now the third NFA, forget about it because you can see this DO. The third NFA is not in the race. Okay, the third NFA is not in the race. So you forget about third NFA. That is not in the race. But remember one thing, the last matching point, that is this. So if there is no longer, if I do not find any longer match, then remember, I will come back, I will backtrack, and I will find the last matching expression, and I will generate a token for the last matching expression. Okay, so this is a marker that this is the last matching expression. Now you can see when you read this DO, then forget about the third NFA, that is out of the race. Okay, in the look at the first NFA. In the first NFA, we are in the final state. Because we are in the final state means now this is the last matching regular expression. Yes or no? So I can remove this marker. There was a marker. That marker I can remove. This is the new marker. Is this clear? This is the new marker. But we will not immediately return this token. Yes or no? We will not say that okay, immediately generate the token DO. No, we will keep reading because we will go long. So you can see when you read this O, now forget about the first NFA, that is out of the picture. Okay, the third NFA out of the picture. The second NFA, we are here, but this is in the race, but this is not in the final state. Yes or no? This is in the race. This regular expression is in the race, but this is not in the final state. So we will read the next character B. Now we are here. Now we will read the next character, that is D. But here you can see in the second NFA, the next character is I. So it means this second NFA is stuck. Yes or no? This second NFA is stuck. Where it is stuck? Here. Here I can say it is stuck. Okay, here it is stuck. The second NFA is stuck. So what we will do now, tell me, because second NFA is stuck, and basically all these NFAs now they are out of the race. Okay, all these three NFAs now they are out of the race. We are standing here. So tell me what we will do. We will go back because all the NFAs are out of the race. Okay, they all are stuck, I can say. All are out of the race, all are stuck. Okay, and you can see here in the theory also the same thing I said. When all the automata get stuck, when all the automata are out of the race, then you report the last match. Okay, read this very interesting line. When all the automata are out of the race, means all are stuck, then you report the last match and then restart the search from the last match point. Okay, so you can see in this also what we will do. Just backtrack and go to the last match. Okay, this is the last match. Yes or no? This is the last match. Okay, so because this is the last match, so what we will do? We will generate a token here. Okay, so this TDO, this token we will generate, and then we will restart. Where we will restart? From this point. Yes or no? From this point we will restart. Okay, is this clear? So very simple. So at this point you will restart. Okay, restart all these NFAs. Again, you run all these NFAs in parallel. Okay, so I hope you understood this point. But remember already, because of this last match, this token is already generated. So if you see the output, in the output, this do token is already generated. Okay, very simple. Now, of course, what you will do after this, you will restart. Okay, you will start from here. Now you will read this character U. Okay, run all these NFAs in parallel. So you can see the first NFA is already stuck because in the first NFA, the first character must be D. So this is already stuck. The second NFA is stuck. In the second NFA, the first character must be D. That is also stuck. But the third NFA will be in the final state. Yes or no? The third NFA will be in the final state. You can see this is stuck. You can see this is stuck. Okay, they are stuck. But the third NFA, that is in the final state. Okay, now we will not stop. We will read the next symbol. When you read the next symbol, all these three NFA, they are stuck. Yes or no? Is this clear? And one more thing, when you read this U, you can see the third NFA is in the final state. So you put a marker, this last match marker you put, that this is the so far, this is the last match. So far, this is the last match. But you don't stop here. What you will do? You will go long. So you will read the next character. Now, when you read the next character, UB, now all these NFA are stuck. Okay, now I can say this is also stuck. All these NFAs are stuck. And when all the NFAs are stuck, then what you will do? Then you will go back and you will find the last match. Okay, yes or no? So that's it. For this last match, you will generate token. Okay, so you can see the output that you have. First, you have this do token, then you have this mystery token. Okay, understood? Please tell me. I hope you are finding this interesting, right? Okay, did you understand? The same way we will go. Okay, then you can see where we will start. Already this is done, then this is done, then we will start from here. Okay, so you can see we will start from here. Then we will run, we are going to run all these NFAs in parallel. So this symbol B, you can see the first NFA is stuck because in the first NFA, the first symbol must be D. The second NFA is stuck. In the second NFA, the first symbol must be D. So both these NFA, they are stuck. But the third NFA, that is in the final state. So because that is in the final state, here you can put a marker. Okay, this is the last match so far. So far, this is the last match. Okay, so far, last match. Because the third NFA is in the final state. So this is so far the last match. But you will not stop here. You will go long. So you will read the next character. BD. Now all these NFA are stuck. Because all these NFA are stuck, so you go backtrack. Okay, in the backtrack, you find the last match and you generate the token. Okay, so you can see the output. That will be, you can see, first you have do token, then you have mystery token. Then again you have mystery token. Okay, for the last match, you will generate the token. Very simple. Okay, then where you will restart, then you can see here you will restart. Okay, now what you will do? Now you will read the symbol D. You will run all these NFAs in parallel. The first NFA, when you read symbol D, when you read character D, the first NFA will be here. The second NFA will be here. The third NFA will be here. Because third NFA is in the final state, so you can put a marker here. Please understand. Okay, put a marker here that this is the T mystery. This is the last. So far, this is the last match. Because remember, the third NFA is in the final state. So because of that, this is the marker. I will put a marker that okay, this is the so far this is the last match. But remember, the first two NFA, they are in the race, but they are not in the final state. They are in the race. Now you can see you will go long. So you will read this O. All these NFA, all these three NFA, they will read O. So the first NFA will go to final state. The second NFA will go here. The second NFA is in the race, but it is not in the final state. The third NFA is stuck. Okay, because in the third NFA you cannot read DO. So the third NFA is stuck. But remember, interesting thing that the first NFA is in the final state. So because the first NFA is in the final state, here this previous marker I can remove and I can put a new marker. A new marker I can put, that is DO. Okay, this new marker I can put. Now remember, this is the so far last match, this DO. Okay, but I will go long. So you can see you will read U. When you read U, then the first NFA is stuck. Yes or no? First NFA is stuck. The third NFA is stuck. What about the second NFA? The second NFA will go here. Then you will read B, second NFA will go here. The first and third NFA is stuck. When you read L, the second NFA will go here. First and third NFA is stuck. When you read E, you will go to final state. Okay, the second NFA will go to final state. Because the second NFA will go to final state, so the previous marker I can remove. Okay, yes or no? the previous marker we can remove. Let's remove it. Okay, because now the second NFA that is in the final state, and because of longest match, now I can say that this is the last match. So far, this is the last match. Okay, and now you can see because the character stream that is ended, so I can say that this token will be generated. That's it. I hope you understood this point. The algorithm, did you understand? Let me know. So you can see this is what will happen finally. So remember, for this same example, I have solved it in two ways. One, using only regular expression without creating NFA, we have solved this question. And the second method, we have converted regular expression to NFA, and then we are running all the NFA in parallel. Okay, and when all the NFA get stuck, then we will go back to the last match. Okay, and we will generate a token corresponding to the last match. So for the same example, we have seen two methods. One method, directly we are using the regular expressions, and another method we are using the NFA. Which did you like more? I hope you understood both of them. That is one thing. Did you understand both of them? The second method, this NFA running, this is an interesting method, I know, but this is time consuming. So in the gate exam, whenever there is any question, then remember what you do, you directly solve the question from the regular expressions. You do not have to create the NFA, you do not have to create the DFA. But actually, the lexical analyzer will create the NFA, then it will convert to DFA. These things will happen. I will tell you. Don't worry. As we go in this lecture, by the end of this lecture, everything will become very clear what the lexical analyzer will do. But as a human being, you are solving the question in the gate exam, in any exam, then how you should solve? That is what I'm telling you. That whenever some question comes in front of you, okay, then you don't have to become a robot. You don't have to do the way lexical analyzer will do. The lexical analyzer will convert the regular expression to NFA. We don't have to do that. As a human being, as a intelligent student, what you can do, you can directly solve the question from the regular expressions. Okay, I hope you understood both of them, both the methods. Please tell me, is this clear so far? Now let's see the challenge number 2. This is, even with the longest match, if two regular expressions apply, means you have already taken the longest match, even with the longest match, two regular expressions are matching, then what to do? Let's see example. With example, this challenge, you will understand what is the problem, you will understand. So let's see. These are the three tokens, and these are the corresponding regular expressions. Now consider this stream of characters. This is the character stream. So let's see how the tokenization will happen. Okay, you will read the characters from left to right, one character at a time. Yes or no? So when I read this D, then tell me which regular expression is in the race. Remember here, these are the three tokens and these are the regular expressions. Please understand, here you have DO, here double, and here notice this is the identifier, means letter followed by any sequence of letter or digits. Okay, and remember this underscore, this is treated, we treat this underscore as a letter. Okay, so remember this is the identifier regular expression. Okay, now you tell me, when you read this character D, from left to right, we are reading characters one by one. So when I read this character D, which regular expression is in the race? All of them. Yes or no? All of them are in the race. So we will read the next character. Now you tell me DO, who is in the race? All of them are in the race. But remember, because this DO, this is matching. So let me put a marker here. Okay, let me put a marker. TDO. This marker I am putting, basically so far, I can say that so far, this is the last match. Is this clear? Is this clear? This is the so far, this is the last match, because you can see this is already matching. This DO, this is already matching. But remember, these are in the race. Actually, this is also matching. Okay, you can see this identifier, this is also matching. This DO, this identifier is also matching. Okay, I will tell you. Here you can notice so far This is also matching. This identifier is also matching. Yes or no? Notice in the identifier, any letter followed by any sequence of letter or digits. So you can notice here actually this DO and this identifier both are matching. But for a moment, let me write this DO token here. I will tell you why. At the end, it will become clear. Okay. So now you can see we will go along. Yes or no? So we will read this DOU. Now you can notice these are matching. These two. Okay. These are in the race. Sorry, they are not matching actually. I can say this is matching, but this is in the race. You will read B. This is matching. This is in the race. Okay. Notice one more thing. When you read this B, at this moment, when you read this, see, notice when you read this U, now you can see that this regular expression is matching, right? This third regular expression is matching. So this you can remove. Okay, this marker you can remove, and you can say that now the last match, that is a identifier. Okay, this is the last match so far. Okay, is this clear? Now when you read this B, now this third regular expression is matching. So you can remove this, and you can say that okay, T identifier that is matching. This is the last match. When you read this L, DOUBL, now remember this is in the race. The second regular expression is in the race, but the third is matching. So because third is matching, you can remove this, and here you can put a marker TID. Okay, identifier. This so far this is the last match. Now you can see when you read this E. Now this is also matching. This is also matching. Both the regular expressions are matching. Yes or no? Okay, you can notice for this we have gone longest match. Okay, now you can notice that here you can remove this, and you can say two are matching. What two are matching? Tell me. You can see this T DO is also double is also matching. Okay, and you can see this T identifier is also matching. Okay, so remember we have taken the longest match, but even with the longest match, two regular expressions are matching. So tell me, for which of them should I generate the token? How to solve this problem? Did you understand the problem? This is the problem number two, that even with the longest match, you have taken the longest match, but still two regular expressions are matching. Now what to do? Tell me. You can see we have taken the longest match. This entire character stream that is matching with this double token, or I can say this double regular expression, also this identifier regular expression. So which of them, for which of them should I generate the token? Let me tell you the answer. In this situation, we will use the priority. There is something called priority. We will assign priority to the tokens. And by default, the token that we write first, that is high priority. Basically, this is the by default order of priority. You can notice there is a problem here. Yes or no? Should I generate this double token? Should I generate this identifier token? You can notice there is a problem here. Which to generate? Which to generate? I can say this is a problem. Yes or no? Okay, so for this problem, let's see what is the solution. Let's see what is the solution for this problem. For this problem, the solution is priority. Very simple. You can see even with the longest match, first you will go with the longest match, but even with the longest match, if two regular expressions match, then choose the one with more priority, with high priority. And let me tell you, by default priority system, if nothing else is given in the question, then by default priority system, you can see priority system, that is pick the rules, pick the rule which is defined first, or I can say listed first. Means when you are writing the rules, the regular expressions, then basically on the top, the regular expression, the token that you have, that has highest priority, and this is the order of priority. Basically the priority is decreasing. Okay, if something is listed first, by default that has high priority, higher priority. Okay, I hope you understood. So in this question, what will happen? what is the solution here? You can notice for this longest match, even after the longest match, these two regular expressions are matching. You can see this blue also and this green also. You can notice this blue also, this green also. Very beautiful slide. Okay, color, you can see the color. This is the blue, so this is the blue. You can see this green is also matching. So even after taking the longest match, two regular expressions are matching. So for which of them should I generate the token? The answer is you will use priority, and this is the by default order of priority, means the priority will decrease from top to down. I can say by default, the rule that you are listing first, the rule that you are writing first, that has more priority. So in this you can see the priority decrease. Okay, I can say this has more top priority, highest priority, and this has lowest priority. So even after the longest match, if multiple regular expressions are matching, then in this situation, you will generate the token corresponding to that regular expression which has higher priority. So for this question, the answer will be this one. Okay, means what will be the output? The output will be this double token will be generated. Okay, is this clear? Very simple. I hope you understood this point. So you can read this: when two regular expressions are matching even after the longest match, if two regular expressions are matching, then choose the one with greater priority. And this is the simple priority system, by default priority system, that is pick the rule which is defined first or listed first. Very simple. I hope you understood this point. Now you tell me, longest matching and priority, first who will come in the picture? Longest match and priority, first who will come in the picture? First, what you will check? First, you will always go long. Longest match, first you will go long. Okay, now even after going long, even with the longest match, if there is tie, if multiple regular expressions are matching, then you consider the priority. Okay, please understand, do not consider priority over the longest match. First you go long. Okay, first you consider the longest match. Then after that, even after the longest match, even with the longest match, if there is a tie, if multiple regular expressions are matching, then you consider the priority. I hope you understood this point. Now let's see the next challenge, that is challenge number 3, that is, what if nothing matches? What if there is no match? Very simple. So in this situation there will be lexical error. Okay, so you can see what if nothing matches? Then the solution is that we will report lexical error. With example, this will become clear. We are going to take a lot of questions, a lot of standard questions now, but I hope you understood the concept so far. So remember the challenges in the scanning. These are the two questions. Let's see the answer to these two questions. Let's see the first question, that is, how do we determine which lexemes are associated with each token? For each token, what is the lexeme associated? How do we determine that? Can you tell me? Very simple answer, using regular expression. Yes or no? We have already seen. So you can notice that how do we determine which lexemes are associated with each token? Okay, so what is the answer here? Using regular expressions. You can see, using regular expressions, we will specify the lexeme pattern corresponding to a token. Okay, so using the regular expression, we will specify token. So the answer will be regular expressions. This is the answer to this question. Okay, now let's see the next question, that is, when there are multiple ways to scan the input, how do you know which one to pick? Okay, when there are multiple ways to scan the input, then which way should we pick? What is the answer for that? We have already seen the solution. First, you go long, means first you see the longest match. First, you consider the longest match. After the longest match, also, if there is tie, even with the longest match, if multiple regular expressions are matching, then we will pick the first rule, that is matching. Okay, means the highest priority rule that is matching, that is what we will pick. Okay, very simple. I hope you understood. So remember, if you see, if you see this if, okay, in your code, if you see this, then tell me what you will do. If you see this, let me know. Will you do this? That okay, there is two keyword if. Will you do like this? That there are two keywords, or will you go long? I told you go long. Yes or no? So remember, there will be a single identifier. If so, this is correct. Okay, is this clear? And what will be the token? The token will be identifier. Okay, is this clear? So remember, this is correct and this is wrong. I hope you understood this point. One more thing, if you only have this if, now this is matching identifier also, this is also matching the keyword, yes or no? So should I generate the keyword token or should I generate the identifier token? Now you can see here, even with the longest match, you have already gone long. Even with the longest match, multiple regular expressions are matching. So here you will consider the priority. So because this is the more priority, this keyword has more priority. Or I can say, when you write the regular expressions, when you write the tokens, you will write keyword first, you will list it first, and then at the end you will list the identifiers. So you can see this will be the answer, this will not be the answer. I hope you understood this point because this token has more priority. Okay, very simple. Now we are going to solve a lot of standard practice questions and also the gate question. We will do the complete analysis of all these questions. All these questions are taken from standard top universities. And let me tell you, one of these questions came in the gate exam also few years back. Okay, that also we will solve. But let me tell you, this gate question is actually, this has come from these standard questions that we are going to solve. Okay, one of these questions has come in the gate exam that we are going to solve. Okay, so let's start now. Let's solve this question from Stanford University. The question is saying, given the following tokens and their associated regular expressions, these are the tokens, three tokens are there. And see, these are the tokens, token 1, token 2, token 3, these are the three tokens, and these are the associated regular expressions. Okay, tokens, associated regular expressions. Show what output is produced if this flex scanner is run over the following strings. Basically, this is the scanner, this is the lexical analyzer, or I can say this is the specification, and these are the input strings, input character stream. So the question is asking what will be the output. Now let me explain what is this flex, because this word you will see many times in the standard university questions. This word you will see in the gate exam, you will not see this word, but this word will come in front of you whenever you are solving many standard university questions. Okay, so let me explain what is this flex. This is a very simple point, this is not required for the gate exam, but let me explain what is this flex. So basically, this flex is basically a fast lexical analyzer generator. Okay, it is basically a software, or I can say it is basically a project. To this project, what you do, to this software, what you do, you just give your specification. Means this is what you do. This is what you give as an input to the flex. Flex is a project, or you can say this is a software which will generate lexical analyzer. Flex is not a lexical analyzer. You can see flex itself is not a lexical analyzer, but it will generate lexical analyzer based on the specification that you provide. So let's assume that you want to create a small lexical analyzer as your college project. Okay, in the compiler design lab, your professor tells you that design a small lexical analyzer. Okay, then you can see, let's assume this is the specification. You want only three tokens, and these are the corresponding regular expressions. So this is the specification that we have. So what you do, you give this specification to the flex. Okay, you give as an input to this flex. This flex is basically a lexical analyzer generator. Okay, what this flex will do, let me tell you. When you give the input to this flex, okay, you can see you specify the specification. Basically, you give the specification as an input to this flex, and what it will do, this will take your specification, read this software, this flex project or software, it will take your specification, means this specification, this will be the input, and it will generate combined NFA. I told you, if you remember, that for every regular expression we will generate NFA. For this we will generate NFA. For this we will generate NFA. For this we will generate NFA. And these three NFA we will run in parallel. So what we can do, these three NFA we can combine. This is what this flex software will do. It will combine these NFA. For every regular expression it will generate NFA. Then it will combine all these NFA. Then it will convert this NFA, the combined NFA, it will convert this combined NFA to equivalent DFA. In the theory of computation subject, we study all these concepts: how to convert regular expression to NFA, how to convert NFA to DFA. So you can see this combined NFA will be converted to DFA. Then we will minimize this DFA. This flex software, this flex project will minimize the DFA as much as possible. And then this DFA that you have, this is your lexical analyzer. Finally, this DFA that you will get, this is called lexical analyzer. Okay. If you want, you can generate C code also corresponding to this DFA. Okay. So remember what this flex software will do. To this flex software, you just give your specification. Okay. Token, regular expression, token, regular expression, token, regular expression. This specification you give because you want to generate a lexical analyzer. What this flex will do, for every regular expression it will create NFA. Okay, for every regular expression NFA will be generated. Then these NFAs will be combined like this. Okay, you can see by null move. Okay, null move, you can see this is NFA1, this is NFA2, this is NFA3. So you can see like this, a combined NFA will be created. This is the combined NFA that will be created. Then this will be converted to DFA. Then this DFA will be minimized. You will get minimal DFA. Let me tell you, this minimal DFA is your lexical analyzer. If anyone asks you what is the lexical analyzer, in one line you can say that lexical analyzer is the DFA. If someone asks you what is lexical analyzer, you can say lexical analyzer is deterministic finite automata. That's it. Chapter over. Okay, is this clear? Did you understand what is happening here? You have a specification, like these are the tokens and these are the corresponding regular expressions. Okay, this flex software, this project, what it will do? It will convert all the regular expression to corresponding NFA. Then combined NFA will be generated like this using the null move. You can see NFA1, NFA2, and this is the start state, and these are the null moves. So this combined NFA will be converted to DFA, and this DFA will be minimized. And finally, this DFA is basically your lexical analyzer. Now, from this DFA also, what we can do, what this flex will do, this flex software, from this DFA also, a C program will be written. And this C program, this is your lexical analyzer. That's it. You can use this C program and you can say that, Professor, this is the lexical analyzer I have created. Okay, is this clear? My project is over. So like this. I hope you understood the point. But here, the interesting thing is that if someone asks you what is lexical analyzer, you can say lexical analyzer is a deterministic finite automata, because overall this DFA is created. Okay, this DFA you can convert to C program if you want, but overall this DFA, this is your lexical analyzer, I can say. I hope you found this interesting. Okay, you can convert this DFA into a C program also. That also will be done by this flex software. Okay, and this C program, you can say that this is my lexical analyzer. Okay, anyway, this is not required from the gate exam point of view, but I just want to tell you that lexical analyzer is basically a deterministic finite automata. I hope you understood. Okay, now let's come back to this Stanford question. Let's solve it. So this is the specification for a lexical analyzer. We have three tokens: token 1, token 2, token 3, and these are the corresponding regular expressions. These are the input character string, or I can say character stream, and we need to find what will be the output. So let's solve all these three questions one by one. So first, let me consider this character stream. This is the input character string or stream. So you can see this A, then your B, C, C, A, then 3 times B. Okay, let's solve it. Let's find what will be the output. Means how the tokenization will happen. What will be the output token stream. So we will read this character stream. This character string, we will read from left to right, one character at a time. Okay, here you can notice. First of all, you understand these regular expressions. So let me explain this regular expression A star B. Star means 0 or more times. Okay, so if you take this 0 time, then you will get B. If you take 1 time, you will get AB. If you take 2 time, you will get AB. If you take 3 time, you will get triple AB. Is this point clear? You can see what this star means. This star means 0 or more times. This star means 0 or more times. Okay, so here you can see if you take it 0 time, then basically you will get B. If you take it 1 time, you will get AB. 2 time AAB. 3 time triple AB, like that. Okay, next you see this regular expression here. A or B whole star means any sequence of A comma B. Remember, this means or. Okay, this vertical line that you have, this is called or. So this is basically A or B whole star means any sequence of A comma B. Star means 0 or more. So remember, any sequence of A comma B, but it should end with B. Okay, so I can basically say that here I can say ending with B. Ending with B. Okay, and here you can see this C star. It means star means 0 or more times. So this C star is basically any number of C. Okay, is this clear? Any string of C's. Okay, any string of C's. Very simple. Now, let's come back to this string. So for this string, what will be the tokenization? We will read this string from left to right, character by character. When you read this A, tell me which regular expression is in the race. When you read this A, you can see the first regular expression is in the race. This regular expression is not in the race. C star, yes or no? Because C star means any string of C's, only C's. Either no C or 1C or 2C or CCC or CCCC, like that. Okay, so you can see that when you read this character A, then which regular expressions are in the race? The first two. Yes or no? The first two regular expressions are in the race. Any of them is matching or not? So far, at this moment, the first two regular expressions are in the race, but any of them is matching or not? So far, they are not matching, because you can see here also the last symbol is B, here also the last symbol is B. So far nothing is matching. So far there is no match, but both the first two regular expressions, they are in the race. So you read the next character. Okay. What about this double A? You can see they are in the race. So which of them are in the race now? Double A. Yes, both are in the race. Yes or no? You can see the first regular expression is also in the race, double A. The second regular expression is basically ending with B. So it is also in the race, because ending with B. So you can have, for example, AAB, you can have AABB, something like this. These things you can have. Okay, so please understand, so far also the first two regular expressions are in the race. Any of them is matching? Let me know. So far, is there any matching? No, nothing. Okay, there is no match so far, but the first two regular expressions are in the race. Okay, now let's read this character also. What about this triple A? Which regular expressions are in the race? Again, both of them are in the race. The first two regular expressions are in the race. Is anything matching so far? Any regular expression is matching so far? No. Okay, so you read the next character. Triple A B. Now you tell me which regular expressions are in the race? Both of them, the first two regular expressions are in the race. Is anything matching so far? Yes, yes, yes. Put a marker here. Put a marker, because yes, there is a match. The first regular expression is also matching. The second regular expression is also matching. Yes or no? Okay. Is this clear? The first and second, both the regular expressions are matching so far. So just put a marker of the last match. Okay, now you tell me. Actually, these two regular expressions are matching so far. The first and second. So you tell me here, when you put this marker, then which regular expression you will put in the marker? You will consider the priority, yes or no? Because you can see for this character stream, the first two regular expressions are actually matching. They are in the race also, they are matching also. Okay, so you can see that because of priority, this A star B, I can say token 1, I will put here. But remember, this is not in the output. This will not go to the output because we will do the longest match. We will keep going. We will go long. Okay, but this is just a marker. Please understand. This is just a marker of last match so far. Okay, last match so far. This is just a marker of last match so far. Okay, of course, here you can see that there is T1 also, means token 1 also, token 2 also. But you can see because of priority, this has highest priority. Okay, so because of that, we will select it. Okay, because of this, this is not chosen, not chosen as the last match point, as last match point. Okay, this is not chosen as the last matching point. Is this clear? Now you go long. Okay, your output has nothing so far. Now you will read this C also. Triple A, B, C. You tell me who is in the race now? No one is in the race. Yes or no? Because you can see here you don't have any C. Here you don't have any C. Okay, so no one is in the race. Do you agree with me? When you have triple A, B, C, now you can see all these three are out of the race. Because all are out of the race, so we will go to the last match point. And when you go to the last match point, this is the last match point. So for this, you will generate a token. So finally, what we will do, we will return. Which token we will return? We will return the token 1. Okay, I hope you understood. Now again, we will restart from here. Is this point clear? Tell me. Now, what we will do, we will restart from here. Now, here you restart. Okay. So, let's do on the next page. So, you can see for this string A, B, C, A, triple B. Okay. So far what we have seen that this is the lexeme, and for this, the token is already generated. Okay, so you can see in the output, this we will print 1. Okay, so we have already printed 1. Okay, so this is the lexeme that we already found. Now we will restart from here. So when you restart from here, you tell me, you will read C. Tell me who is in the race. The first two are not in the race because there is no C here. In these two regular expressions, you don't have any C. So only this third regular expression is in the race. And it is matching also. Yes or no, C star means any sequence of C's. Okay, so you can say that, okay, here you can put a last matching point. Okay, but anyway, you already know that this is the last matching point. Then you will read this C. Then yes, this is also matching CC. Then you will read this A. Now you can see nothing is matching, so you will go to the last matching point. Yes or no? So remember, for this CC, what you will do? You will print 3. Okay, yes or no? You will print 3. Very simple. So this is the next lexeme you got. Now you will restart from here. Okay, now you can see when I read A, now this third regular expression is out of the race. Who is in the race? These two are in the race. So you will read B. Who is in the race? After A, there is B. Who is in the race? Both of them are in the race. Yes or no? The first and second both are in the race. And you can see that both are matching also. So if you want, you can put here, you can put a marker because you can see both these are matching. So you can put a marker if you want. Okay, so you can put a marker that, okay, that token T1 is matching so far. This is the marker for last match so far. Okay, Now you can see we will read the next symbol B, A, B, B. Now you can see who is in the race. Now this first regular expression is out of the race because in the first regular expression you cannot have more than one B. So this first regular expression is out of the race. But the second regular expression is in the race because second regular expression says that ending with B. Yes, it is ending with B. Yes or no, A, B, B. This is ending with B. So now you can see that it is matching also. This second regular expression is matching also. So this marker you can remove. This marker you can remove and you can put a new marker. Okay, you can put a new marker that okay that this token T2 will be generated. This is the new marker. This is the marker for last match so far. See, this question actually you can solve very quickly, but just for understanding purpose, I'm providing you the complete explanation. But of course, you can solve this question very quickly. Okay, next you can see when you read this B, now, okay, here, that's it. You can see only this regular expression is matching. Okay, means we will generate token T2. Yes or no? Token T2 will be generated. Okay, so here you can see 132. This will be the answer. Okay, is this clear? This will be the token stream. This will be the output. So this will be the answer for this input string. This will be the output 132. I hope you understood this. Let's solve for this second string. For the first string we have already done. Let's see for the second string. So you can see the second string is C, B, 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 4 times B, then there is AC. Okay, so let's read this character string from left to right, character by character. So you can see when I read this C, which regular expression is in the race? Only this third is in the race. These are not in the race, first two, because there is no C in these regular expressions. Yes or no? Now, what about this CB? Now you can see all are out of the race. So what was the last matching point? The last matching point was this C. Yes or no? Okay, this C is the last matching point. So here I can say you got our lexeme. The first lexeme you got. Okay, so the output will be what? The token that will be generated, that will be 3. The token 3 will be generated. Okay. Now you can see you will read this B. Who is in the race? Which regular expression is in the race? You can see the first two regular expressions are in the race. The third regular expression is not in the race because here you don't have any A comma B. So when I read this B, then the first two regular expressions are in the race. Now I will read the next B. Who is in the race? Now this first regular expression is out of the race because here you only have one B at the end. There is no more B. But here you have ending with B. Yes, this is ending with B. Then you will read the next B. Yes, this is ending with B. Only this second regular expression is in the race. Then you will read this B. This is ending with B. Yes, this second regular expression is in the race. Only the second regular expression is in the race. Then you will read this A. Now you can see that when you read this A, now this is not ending with B. Yes or no? Now this is not ending with B. Yes or no? Okay. Okay. Then next there is C actually. Now you can see this is also out of the race. Please understand that when you see this 4BA, then this is not matching the second regular expression, but second regular expression is in the race now. Okay. Yes or no? Please understand. See, so far here, till here, the second regular expression was matching. It was in the race also, it was matching also. Okay, then when you read the next symbol now the second regular expression is in the race, but it is not matching. The second regular expression is in the race. You can see any sequence of A comma B, any sequence of A comma B followed ending by B, ending with B. So you can notice that till now, till here, the second regular expression was in the race also, it was matching also. But when you read the next symbol, then here the second regular expression is not matching, but it is in the race. Then when you read this, now the second regular expression, this is out of the race. So you will go back and you will find what was the last match. The last match was here. Yes or no? This was the last match. So here, this is the lexeme that you got. Okay, I will print 2. Token 2 will be generated. Okay, then you can see I will restart here. Okay, I will read this A. Who is in the race? The first two regular expressions are in the race. When I read this C, Now you can see all of them are out of the race. All these regular expressions, they are out of the race. So you will go back and you will find what was the last match. This was the last match. So this is our next lexeme. Now you can see there is a problem here. There is no match. Notice one thing, very simple here. I am saying that first you read this symbol A, then these two regular expressions are in the race. Then you read the symbol C. Now all the regular expressions, they are out of the race. So we will go back to the last match. But remember, there is no match here. This A, this is not matching here. This is not matching here. Here also you should end with B. Here also you should end with B. So please understand that you will go back, but there is no last match. Because there is no last match, so here what I can do, tell me. There is no match possible now. Yes or no? There is no match, so that's it. I can say there is lexical error. Okay, is this clear? Let me know. So because there is no match, so here I can say that we will get lexical error. We will get, means tokenization not possible. The lexical error that we will get, I can say that is basically tokenization not possible. I hope you understood this. Very interesting example. Please tell me, did you understand? Because please understand that this A, this is not matching with any of these regular expressions. The first regular expression also, you can see the last symbol should be B. Here also the last symbol should be B. So you can see that there is no match. So there is lexical error. Tokenization is not possible. Okay, so for this second one, tokenization is not possible. Okay, so basically the output will not be this. The output will be, this will be the output, the lexical error. I hope you understood. Now let's see the third one, that is CBABC. What about this string? Let's read from left to right, character by character. When you read this character C, which regular expression are in the race? Only the third regular expression is in the race, because in the first two regular expression there is no symbol C. Okay. Now when you read this CB, now all the regular expression, they are out of the race. So what was the last matching point? What was the last match? Yes, this C is match. This C is matching. Yes or no? So I can say the output. In the output, I will print the token 3. Okay. Yes or no? This is the lexeme I got. I got my first lexeme. Now you can see we will start here. Okay. When you read this B, then which regular expression is matching? First two regular expressions are matching. Then you will read A. Which regular expression are in the race? When you read BA, then which regular expression are in the race? The the first regular expression is out of the race. The third is also out of the race, but second is in the race. Okay, because in the second you can see any sequence of A comma B, then ending with B. So remember, so far here, the second regular expression is in the race, but it is not matching. It is in the race. Then BAB, second regular expression is matching also, it is in the race also. Then BABC. Now here all the regular expression, they are out of the race. So what was the last matching point? This was the last matching point. You can see this is matching with token 2, regular expression corresponding to token 2. Yes or no? Now you can see finally this C, this is matching with this regular expression only. Only this regular expression is matching. So for this is the lexeme and 3 will be printed. Okay, so this is the output token stream. The answer will be 323. Is this clear? So overall, let me tell you what will be the output for this, for the first, for the second, and for the third. What will be the output? Can you tell me? You can see the answer here. I have already provided the answer. For the first, the answer was 132. Did we get the same answer, 132? Yes, we got 132. For the second, you can see the tokenization is not possible. Okay, so there will be error. The tokenization will not be possible. You can see there is no match. So there will be error. On the screen, on the console, there will be error message, lexical error, tokenization not possible. And for the third string, the output will be 323. I hope you understood this question. Very easy. Let's solve this question from the Stanford University. Another very simple question. The similar question we have already done. So let's solve this question also. Give the Given the following tokens and their associated regular expression, these are the tokens, token 1, token 2, token 3, and these are the corresponding associated regular expression. Show what output is produced when we run the scanner on this string. So this is the input string, and what will be the output? What will the lexical analyzer print? Means what will be the output token stream? Okay, so let's see this character stream. We have input character stream, that is A, B, C, A, C, A, C, double A, C, A, C, double A. Okay, so let's see here. First of all, you understand all the regular expressions so that you can solve this question very quickly. Okay, in any similar question, you should first understand the regular expressions so that you can solve the question very quickly. You can see the first regular expression, that is basically A star B, means any sequence of A's ending with single B. Yes or no? This is simple CA, that's it, nothing else. Okay, here you can see this is basically only one lexeme, I can say only one pattern, that is CA. But here you can notice there are many. This star means zero or more times. If I take it zero time, I will get B. If I take it one time, AB, AAB, and so on. Okay. Now, what about this here? You can see this is A star, C, A star. Means definitely there should be C. Okay. Surrounded by A's. Means C is also fine because star means zero or more times. This star also means zero or more times. Remember, this star has nothing to do with this star. So, for example, this star you can take 2, this star you can take 4. Okay. So, you can see if I take both the stars 0, I will get C. I can also get AC. I can also get CA. I can also get AAC. I can also get ACA, and so on. Okay. These things. Very simple. Okay. Now, let's see here. For this input, let's read it from left to right, character by character. When I read this A, which regular expression are in the race? The second is not in the race because you can see the second regular expression, it has only one string, that is CA. That is also starting with C. Okay, so when you read this character A, then the first and third, they are in the race. Okay, what about this B? Is there anything in the race? A, B. Now this third is out of the race because you can see in the third regular expression you don't have any symbol B. Now you can see only the first regular expression is in the race. Now when you read this C, now all the regular expression are out of the race. So you go back and you find the last match. This AB, this is the last match. This is matching with the token 1, regular expression corresponding to token 1. Yes or no? So remember, this was the last match. So what will be the output? What the lexical analyzer will print? First, it will print the token 1. Okay. Now let's again read from here. First, you read this C. Which regular expression is in the race? You can see the first regular expression is not in the race because in the first regular expression you don't have symbol C. The remaining two regular expression, they are in the race. What about CA? Yes, these are in the race. What about C double A? You can see the second regular expression is not in the race, but third regular expression is still in the race. Now you have another C. Now all the regular expression, they are out of the race because in the third regular expression you don't have multiple C. Okay, so here you can see all the three regular expression are out of the race. So you go back and you find the last match. You can see this was the last match, longest match. Always take the longest match. Don't say that okay, CA means print 2. Okay, always find the longest match. Some students, what they will do, they will see this CA, and for this CA they will print 2. But remember, this C double A, this is the longest match, and we will print 3. Okay, very simple. So another lexeme we got. The first lexeme is AB, another next lexeme, that is C double A. Now again you read from here. Who is in the race? Which regular expression is in the race? The second and third regular expression, they are in the race. CA, yes, these are in the race. These two regular expression are in the race. CAC, all the regular expression, they are out of the race. So you go back and you find the last match. Is this the last match? This CA, is this the last match? Yes. Now remember, this CA, this is matching with this regular expression also. The second and third, both the regular expression, it is matching. Yes or no? This CA, it is matching here also, it is matching here also. You have CA here also, you have CA here also. So tell me, what token should be generated? Now the priority will come into photo. Priority will come in the picture. So you can see by default, the priority will decrease from top to down. Yes or no? The rule that we list first, the rule that we write first, that has more priority. So you can see for this lexeme, the token 2 will be printed, not the token 3. Okay, priority will come in the picture. We have already seen this. Okay, now let's see this CAA. Okay, now it is very common sense. Okay, very easily we have already seen that. Only this third regular expression will match. The longest match we will prefer. Only the third regular expression will match. So this is our last lexeme, and you can see this 3 will be printed. So this is the token stream. The output will be 1323. This is the output. I hope you understood. So you can see the output will be 1323. Let's solve this question from the Stanford. Consider the following lexical specification. Basically, we have 3 tokens: token 1, token 2, token 3. These are the associated regular expression. What we will get in the output for the string AAB? For the string AAB, what output we are going to get? Let's see. What will be the token stream? You can see this is the input character stream. What will be the tokenization? Let's see. So here you can see we have AAB. Let's read this character string, this input string from left to right, character by character. When you read this first character, which regular expression is in the race? Notice these regular expressions are very simple regular expressions. Here you only have one string, that is AA. This regular expression also have only one string, that is A. This regular expression also have only one string, that is AB. Okay, so you can see when you read this A, then which regular expression are in the race? All of them. Yes or no? All of them are in the race. Now you go for the longest match. So you go long. So you can see for this AA, who are in the race? The first is in the race. The second and third, they are not in the race. The first is in the race. Now you will read the next symbol A, B. Now who is in the race? Now no one is in the race. So you go back and you find the last match. What was the last match? This AA. This is the last match. This is matching with the first regular expression. Yes or no? So from the longest matching, because we will always go for the longest match. So here you can see this is the lexeme we will get. Okay, and corresponding to this lexeme, we are going to print 1. Yes or no? This will be printed. This token will be generated, token 1. Now you can see we will start from here. Okay, now let's read this B. Tell me which regular expression is matching? None of them. Yes or no? So there is no match. There is no match, and because there is no match, so I can say tokenization not possible. Yes or no? Tokenization not possible. Because tokenization is not possible, so I can say we got lexical error. I hope you understood this point. So remember, for this input character string, there will be lexical error. Okay, very simple question. I hope you understood. This is the explanation. You can read it. You can see because of longest match, the first match will be AA, but after that there will be no match. So lexical error. We failed to tokenization. Let's solve this question from Berkeley University. In this question, there are 3 parts: part A, part B, part C. Let's solve this question. Every part one by one. Let's solve. So let's solve the first part of this Berkeley question. You can see, consider the following flex-like specification. Basically, a specification of a lexical analyzer. For a lexical analyzer for a scanner, this is the specification. Basically, these are the tokens and these are the associated regular expressions. You can see the parenthesis. This is not part of input alphabet. Okay. So basically, the input alphabet, that is basically A, B, C. This is the input alphabet. You can see these are the tokens, total 5 classes of tokens we have. Okay, and these are the associated corresponding regular expressions. Show how the following string is partitioned into tokens. This is the input string. We need to find how the tokenization will happen. What will be the output token stream corresponding to this input character stream? Label each lexeme with the integer of the correct token class. These are the token classes. Okay, and this is the string. This is the input string. So let's solve this question. What we will do, we will read this input string from left to right, character by character. Okay, let's read the first symbol A. First, you understand all these regular expressions so that you can solve this question very quickly. You can see this is basically A star, means at least one A. I can also write it A plus. This A plus. Plus means one or more times. Okay, plus means one or more time. Remember, this plus is in the power. This plus we are writing in the power. This is not or. This is clean plus. This is called clean plus. Okay, this we study in the regular expression chapter in the theory of computation subject. Okay, so you can see this is basically at least one A. Okay, sequence of A's. Next, here you can see we start with C, then any sequence of A comma B. Here you can see we are starting with A, ending with C, in between any sequence of B. Here you can see we are starting with CA, then any sequence of A. Here you can notice this B is optional. There must be at least one A, then this A is optional. At the end, either C or nothing. Okay, this epsilon, this is basically empty string. Okay, means nothing. So you understand what are the regular expressions. Now you solve this question very quickly. So when I read this character A, tell me which regular expressions are in the race. Find out which regular expressions are in the race when I read this character A. This regular expression is not in the race. This is not in the race. Do you agree with me? The second and fourth regular expression, they are out of the race because in them the first symbol is C. Okay, so you can see this is in the race, this is in the race, this is also in the race. These three are in the race. So you read the next symbol AB. Now tell me who is in the race. This is not in the race because here you don't have symbol B. Okay, now you can see these are out of the race. When you have AB, after A there is B, then this is also out of the race. Please understand, in the last regular expression, after A you cannot have B. Initially you can have B, but after A there is no B. Okay, so tell me, for this AB, you can notice these are out of the race, these are out of the race. Only the third regular expression is in the race. Okay, after that there is C. Okay, now ABC. Now you can notice only this is in the race. Okay, the remaining are not in the race. Yes or no? ABC. Now after that there is A. ABCA. Now you can notice this is also not in the race now because after CA cannot come. So now you can see ABCA. Now all of them are out of the race. So you go back and you find what was the last match. So you can see this ABC, this is the last match. Do you agree with me? This ABC. This is matching with the regular expression for token 3. Okay, agree? So remember in the output what you will say? You will print token 3. The token 3 will be printed. I hope you understood. Now we will resume here. Okay, let's read symbol A. Who is in the race? This is in the race. The second regular expression is not in the race because the second regular expression and fourth regular expression, they will start with character C. Okay, so you can see when you read this symbol A, then these three are in the race. First, third, and fifth. AB, who is in the race? Again, you can see this is out of the race. This is out of the race. Basically, only this is in the race now. Again, C. So only this is in the race. Then A. Now everyone is out of the race. So you go back and you find what was the last match. Okay, you can see this ABC. This was the last match. Again, token 3 will be generated. Okay, very simple. Now let's see. Now you will resume here. You will read this A. Who is in the race? You already know. This is not in the race. This is not in the race. Now then again A. Who is in the race? Yes, this is in the race. The first regular expression is in the race. The this third regular expression is not in the race. Okay, this is not in the race. This is not in the race. This is not in the race. Double A, because of double A. Because of double A, yes, this is also in the race. Then there is B. After A, there is B. Now this is also out of the race. This is also out of the race. All of them are out of the race. So you go back and you find what was the last matching point. Now you can notice this double A. This was the last matching. This was the last match. Double A. And who was matching? Double A. This is also matching. This is also matching. So tell me, which token should I generate? Token 1 or token 5? Because of this double A, you can see this is also matching. This is also matching. These two regular expressions are matching for double A. So which token should I generate? Token 1, token 5? The answer will be token 1, because priority will come in the into picture. You will decide by priority. And remember, the rule that you are writing first, that has highest priority by default. So remember, the priority is decreasing like this. So token 1 will be generated. I hope you understood. Now let's see the next. B. When you read this character B, now this is out of the race, out of the race, out of the race, out of the race. Only this last expression is in the race. Okay. B, double B. Yes, this is still in the race. The last expression, this is still in the race. BBA. Yes, this is still in the race. BBA. Yes, this is still in the race. Very good. BBAC. Yes, this is still in the race. Okay. Double B, then A, then A, then C. You can do this. Okay. Very good. So you can see. Then double B, double A, double C, now out of the race. Okay, yes or no? When there is double C, now all the five regular expressions, they are out of the race. So you go back and you find what was the last longest match. So the last longest match was this double B, double A, C. Yes or no? Double A, double B, double A, C. So this is matching with the token 5. So token 5 will be in the output. Very beautiful question. I hope you understood the analysis so far. Now let's continue. When you see this C, starting with C, remember, out of the race, because here in the first regular expression, the first symbol should be A. Out of the race, out of the race. Here you can notice you are starting with C. So actually, this is also out of the race, because before C, at least A should be there. Okay, so this is also out of the race. Only two are in the race. This is in the race, this is in the race. Double C, who is in the race? Tell me. All of them are out of the race. Agree? Yes or no? Double C, all of them are out of the race. So you go back and you find what was the last match. Okay, this is the last match. So you can see this C. This is matching here. This is not matching here. Yes or no? Because remember, this fourth regular expression should have C comma A. Okay. So only this is matching, because here you have C. Okay, is this clear? C followed by any sequence of A comma B. So here I can say that token 2 will be generated. Next, this C, you can see this is in the race, this is in the race. Okay. Now after that, you can see CA. Very good. This is in the race, this is in the race. After that, CAB. Now this is out of the race, because in the fourth regular expression, there is no symbol B. But this is still in the race. Yes or no? This CAB, this is still in the race. Then CABA. This is still in the race, because C followed by any sequence of A comma B. Okay, then again C. Now all of them are out of the race. Okay, because here you can see in the second regular expression, C followed by any sequence of A comma B, but after A comma B, C should not come. So you go back and you find what was the last matching point. What was the last match? This is CABA. This is the last match matching with token 2. Very good. Excellent. Now let's see the next. This C. Now, this is in the race, this is in the race. All the remaining are out of the race. CC, all of them are out of the race. So you go back and you find what was the last match. That is basically C. Okay. That is only matching with token 2. Very good. Remember, this C is not matching with token 4, because in the token 4, in the regular expression for token 4, you need CA. There must be first character C, the second character A. Okay, now let's see here. See, this is matching with this regular expression, not matching, actually, they are in the race. Okay, The second and fourth, they are in the race. CB, now this is out of the race. Only this is in the race. The second regular expression is in the race. CBB, yes, the second regular expression is in the race and it is matching also. Okay, so that's it. So for this CBB, what will be generated? Token 2 will be generated. Okay, so the output will be 33152222. This will be the final output for this part A. I hope you understood. Is this crystal clear? Please tell me. You can see this is the answer for the part A. The same answer we got 3315, then all 2, 3315, then all 2. The same answer we got. Let's solve the part B of this Berkeley question. So these are the 5 tokens. These are the associated regular expression. The question is asking in the part B, assume that input alphabet is A, B, C. Are there any non-empty string that do not match any rule? Is there any non-empty string which does not match any of these rules? If there is such example, give it. So tell me, is there any string which does not match any of these rules? Let me give you a hint. To solve this type of question, always start from the minimum length string and go step by step. See, what the question is asking, the question is asking that is there any non-empty string? Okay, means a string of length at least 1. So, do we have any non-empty string that does not match any rule? This is the question. Let me give you a hint to solve this type of question. Because here we have to go through many strings. We have to check a lot of strings, yes or no? You might be thinking, sir, a lot of strings we have to check. I don't know which string will will not match any rule, yes or no? So let me tell you, the hint is very simple. In this type of question where you have to check a lot of strings, you have to check in any this type of question, in any similar type of question where you have to check a lot of strings, you have to check, then always check from length 1 onward, because we are talking about non-empty strings. So start from length 1 onward. Okay, so if first you check length 1 strings, then length 2 strings, then length 3 strings, then length 4 strings, and so on. Like this you solve this type of question. I hope you understood. Okay, so let's consider the length 1 string. What about this A? What about this string? Is it matching any rule? This is your input string. That's it. Only one symbol, one length string. Is it matching any rule? Yes, this is matching the first rule. Yes or no? For this, actually, the tokenization will happen. That will be token T1. Very simple. What about B? Because consider all the one length string. This is one length string A, another one length string is B, another one length string is C. Okay, so let's consider this B. Tell me, for this string B, what will be the tokenization? When you read this symbol B, then this is out of the picture, this is out of the race. The first regular expression, this is out of the race, this is out of the race, this is out of the race, this is out of the race. So when you read B, yes, this is in the race. But this is the complete string, only one length string. But in the fifth regular expression, you must have A. There must be at least one A. So I can say this is also not matching. Yes or no? These are already out of the race and this is not matching. So that's it. We got our answer. Is this clear? So you can see, that's it. This is the answer we got, that okay, for this string, there is no match. Okay, is this clear? There is no rule matching. Basically, I can say for this string, there is no rule matching. Okay, I hope you understood this solution. Very simple solution, and this is the hint I have given to you, that for this type of question where you have to check many strings. Okay, then for this type of question, always start from length 1 string and go on. Okay, because here we are talking about non-empty strings. Let's solve the part C of this Berkeley question. The part A, part B we have already done. Let's see the part C, that is, can any of the rules in this specification, so this lexical analyzer specification is given to us. These are the 5 token classes and these are the associated regular expression. Can any of these rules in this specification can be deleted without changing the lexer's behavior on any string. Means among these rules, can I delete any rule such that the lexer's behavior, the lexical analyzer's behavior will not change for any string at all? Okay, so which rules can be deleted? Maybe multiple, maybe this is MSQ question, maybe multiple rules can be deleted. Okay, this is a very interesting question. Can I delete some rule which will never be used? Basically, the question is asking that among these rules, is there any rule which will never be used? Or I can say, is there any token which will never be generated? This is what the question is asking. Do we have any token here which will never be generated? So if some token can never be generated, so that rule we can delete. Okay. Now to solve this type of question, let me tell you what you do. You go from top to down, because this is the priority order. Okay, this is highest priority, this is the lowest priority. Always go from top to down. Okay, now let me explain this question. So just go from top to down. You just see, will it ever be used? Tell me, this token 1, can it ever be generated? Yes, it can be generated because this has the highest priority. So for example, if you have a string a, if you have this string, then what will be the output for this string? For this string, the output will be token 1. Okay, yes or no? You have one length string a, then for this string, the output will be token 1. So yes, token 1 can be generated. We are looking for that token which can never be generated. Okay, basically, which rule can be removed? This is similar to asking that which token is never can never be generated, can never be generated for any string. This is what the question is asking. Okay, so you can easily see here. I can say that definitely this rule I cannot delete. The first rule definitely I cannot delete. Okay, so you go from top to down. Now, what about this rule? Can I delete it? No, this rule also I cannot delete. Okay, here you can see that. For example, let me give you a string. Consider this string C. That's it. Only C. Consider this string C. For this string C, what will be the output? The output will be token 2. Okay. So you can see that this rule also I cannot delete. Let me tell you what is the concept behind this question. Okay. Instead of going one by one, instead of going like that, let me tell you the concept behind this question. Notice one thing. This is the priority order. Okay, means here priority decreases. Just let me tell you, I am going to tell you now what is the concept behind this question. The question is asking which rule can be removed. Okay, means which token can never be generated. Means which token can never be generated for any string. Okay, so here you can see the concept is like this. Notice this. Look at this A, B star, C. Tell me, is this subset of any of the above rules? Is this A star B, A, B star C? Is this subset of any of these rules? No, this is not subset of any of the above rules. Okay, look at this. Is this subset of any of the above rules? This C, A star. Is this subset of any of the above rules? This CAA star. Is this subset of any of the above rules? Yes. This CAA star, this is subset of this rule. Okay, is this notice? Is this clear? Tell me. See, the rule 4 is a subset of rule 2. Do you agree with me? Every string that is there in the rule 4, that is also there in the rule 2. Do you agree with me? Every string that can match rule 4, that will also match rule 2. Agree? Okay, in this rule 4, we have strings like CA, CAA, C triple A, C4A. Any string that can match rule 4, that will also match rule 2. And rule 2 has more priority. Okay, yes or no? Understand the concept. This rule 2, this has more priority. This rule 2 has more priority. Okay, and you can see rule 4 is basically subset of rule 2, because every string that belongs to rule 4, that also belongs to rule 2. Any string that can possibly match rule 4, that will also match rule 2. So if any string, for any string, if you generate token 4, then instead you can generate token 2, because of priority. Actually, you will not generate token 4, you will generate token 2. Do you agree with me? Just understand, for any string, if you are thinking that okay, let's generate token 4 because this string is matching this rule, then this string is also matching this rule 2, and this rule 2 has higher priority. So instead of generating token 4, you will actually generate token 2. Okay, so that's it. I hope you understood the concept. So remember, because rule 4 is subset of rule 2, and rule 2 is has more priority, because we have written the rule 2 above rule 4. Okay, so that is the reason here I can say that rule 4 can be deleted, or I can say that token 4 can never be generated. Okay, rule 4 can be deleted, or I can say that token 4 can never be generated for any string. Did you understand this beautiful question? Tell me, this new variation, did you understand? Token 4 can never be generated. The concept, did you understand? This type of question, maybe in future, this type of question can come in the gate exam. Okay, so very beautiful variation. What about the next? So you can see this we can delete. Okay, so forget about it. This we can delete. Forget about it. This we have deleted. Okay, you tell me, what about this? Is this subset of any of the above rules? This rule, is this subset of any of the above rules? No, this is not subset of any of the above rules. Here you can notice I can give you a string here which will not be generated by any of these rules. Okay, can you give me a string here? Can you give me a string here which will not be generated, which cannot be generated by any of the above rules? Or I can say, can you give me a string here which does not belong to any of the above rules? Can you give me? Yes, for example, let's start with B, then have A. That's it, BA. Okay, you can see this BA does not belong here. Okay, you can see there is no BA here. Is this point clear? So you can see, for example, if your input is BA, let's assume your input is BA, then what will be the output? You can see the first symbol is B. So this is out of the race, out of the race, out of the race. Okay, yes or no? You can see only this is in the race. So because of longest match, basically token 5 will be generated. This will be the output. Okay, so you can see that this string belongs to this rule, and this string does not belong to any of the above rules. Okay, so that is the reason I can say only this rule number 4 we can delete, no other rule we can delete. I hope you understood this explanation. Very beautiful question. I hope you understood. So you can read the explanation here, that rule 4 can be removed. Why? Because any string that can possibly match rule 4, that will also match rule 2, and rule 2 has higher precedence. So we will never use rule 4, or I can say that the token corresponding to rule 4, the token 4 will never be generated for any string. So this is a beautiful question, and I hope you understood the explanation. Let me give you a note here. You can see this is the note. Let me write. See, let me make a diagram here. Let's assume that there is a rule here. There's a rule X. Okay, like this, these are the rules. and there is a rule y here. Okay, now this is the situation. So obviously rule x has higher priority, yes or no? This has higher priority because we have listed rule x before rule y, so this is higher priority, lower priority. Okay, higher priority than rule y. Okay, now here one more thing. If if this y is a subset of x, means any string that can possibly match y, if that will also match x, and x has more priority, in this situation I can say rule y can be deleted. Rule y can be deleted. Okay, that's it. This is the explanation, this is the theorem. You can take it as a theorem if you want, but I hope you understood the concept that in this type of situation where y is subset of x, so this rule y, or I can say the token corresponding to rule y, that will never be generated, so you can delete it. Okay, so you can read this here, that assume rule x is listed before rule y, so rule x has higher precedence, higher priority than rule y. If rule y is subset of rule x, then what it means that every string that can possibly match y, that will also match x. And so in this situation we can remove rule y because it will never be executed, or I can say it will never be used. That's it. Let's solve the next question from Stanford University. Consider the following flex specification, basically the specification of a lexical analyzer that your coworker has written. So basically there are six tokens, six token classes, token 1, token 2, token 6, and so on. You can see these are the corresponding or associated regular expressions. Since you have taken CS 143, this is a course in the Stanford University, so forget about it. You can say, since you have taken goclasses compiler design course, since you have studied from goclasses compiler design course, you immediately spot one or more rules that can never be executed. Which rules can never be executed? Let's find it. Very beautiful question. Here I can say that instead of this, you can say goclasses compiler design course. So since you have taken goclasses compiler design course, since you have watched goclasses compiler design lectures, you immediately you can spot one or more rules you can spot that will never be executed. Which rules can never be executed, or I can say which rules can be removed, basically which tokens will never be generated. One more thing here, there is a formatting error actually here in this question. Let me tell you, there is a formatting error. Okay, actually here this is clean plus. Okay, so let me just tell you, in this question there is a small formatting error. This is actually AC clean plus B star. Okay, this is not or, it is basically clean plus. This is AB star, that you already know, AB star. Okay, one more thing here, this, it is basically AC star B plus. Okay, so this is just a formatting error. Don't worry, this type of formatting error will not happen in the gate exam. So you can see. Now let's solve this question. So I already told you in the previous question, I already told you how to solve this type of question. Which rule will never be executed, which token will never be generated, how to find it, tell me. In the previous question, the complete explanation we have already seen. In the previous question, the concept we have already seen. So you tell me what we will do. We will go from top to down, yes or no, because priority is decreasing from top to down. Okay, so there is no problem here, this will definitely be used. Okay, for example, if your input string that is C only, that's it. Okay, then what will be the output, what will be the tokenization? The token 1 will be printed. Okay, very simple. So you can see you are going from top to down. Okay, just see, this is at the top, so this will this will never be removed, basically this is always useful. Okay, next you can see, what about this A C plus B star, is this subset of this? Do you have any string here which is not present above it? in this regular expression, do you have any string which is not present in the regular expressions above it? Yes, there are many strings here which are not present here. For example, ACB, yes or no, or for example AC. Okay, let me give you example. So you can see, let's assume your input is AC. Now you can see for this input AC, what will be the output? Very simple, token 1 will be generated. Okay, that's it. Sorry, token 2 will be generated. Okay, for this AC. So you can easily notice that here you have some string which is not present above it. Okay, what about this CC? What about this CC? Tell me, is there any string here in this CC? Is there any string here which is not present above it? Do you have any string here which is not present above it? Yes, CC itself. Yes or no? CC itself is not present above it. You can see here there is no CC. Here there is no CC. So I can say this is also useful. For example, if your input is CC, then let me tell you what output will be generated. Output will be generated, that will be token 3. Okay. So you can notice this CC, there is at least one string here, that is CC, that is not present above it. Okay, that cannot be generated above it. Okay, what about the next? What about this AB star? Can you give me at least one string which is present here, which can be generated here, which is not present above it? Can you give me at least one such string? Yes, AB. Yes or no? For example, you can give AB or A double B. Okay, you can notice here above it there is no AB. Okay, do you agree with me? So you can easily see that this is also useful. Let me give you example. If your input is actually AB, then you can easily check. You can try this. The token that will be generated, that will be 4. So you can see this token can also be generated. This can also generated. This can be generated. This can be generated. So far, all these rules are actually useful rules. We cannot remove any of them. Okay, now let's see the next one. What about this A? Is there any string here which is not present above it? Tell me. No, you can see this is actually subset of this. Notice one thing, that here also you can generate A, here also you can generate A. Okay, and you can see that this rule 5, this is actually subset of rule 4. Okay, rule 5 is subset of rule 4. And in the previous question, we have already seen when this type of situation happens, that rule 5 is subset of rule 4. So this token 5 will never be generated. It will never be generated. And I can say this rule 5 will never be executed because rule 4 has more priority than rule 5. So for any string, if rule 5 is matching, then rule 4 is also matching. So definitely because of priority, we will use the rule 4. So you can see because rule 5 is subset of rule 4. So here I can say that rule 5 can be deleted without any tension, without any worry. Rule 5 can be deleted. Okay, so let's delete the rule 5. Okay, from the next slide, let me delete the rule 5. Rule 5 is gone now. Okay, but now you don't stop. You also check for the last rule, and something very interesting is coming. Tell me, this last rule, is this subset of any of the rule above it? You can see this is not subset of this. This is not subset of this. Why? See this A C star B plus. This is not subset of rule 2. You can notice that rule 6 is not subset of rule 2. Why? What is the reason? In the rule 6, you can generate AB, but in the rule 2, you cannot generate AB. Okay, yes or no? So rule 6 is not subset of rule 2. Rule 6 is not subset of rule 1. Rule 6 is not subset of rule 3. And rule 6 is not subset of rule 4. So tell me, can I say this is useful, or still is there any mystery? Is there any trick? Is there any trick involved here? You tell me. Notice one thing, rule 6 is not a subset of rule 1. Rule 6 is not a subset of rule 2. Rule 6 is not a subset of rule 3. Rule 6 is not a subset of rule 4. Okay, is this clear? Now you tell me. So, can I say that rule 6 is useful? No. Can you give me at least one string in the rule 6? Can you give me at least one string which is not present above it, which cannot be generated above it? Very simple question I am asking. Can you give me at least one string which cannot be generated by the rules above it? Simple question I am asking. Give give at least one string generated by rule 6 that cannot be generated by any rule above it. Can you give me? Can you give me any such string that can be generated by the rule 6, but it cannot be generated by any rule above it? Give at least one such string. Let me tell you, no such string is possible. Okay, let me tell you, no such string. Basically, there is no string which rule 6 can generate, but no rule above it can generate. Okay, let me tell you, you can easily prove it. See, in this rule 6, you can make two cases. Either this star you will take 0 or you will take it non zero. Do you agree with me? In the rule 6, notice one thing. In the rule 6, there is case 1. Either the string will be like this, or the case 2, the string will be like this. So you tell me now, there are two cases. In the rule 6, there are two cases. You can notice this star, if I take 0, then it will be AB plus this type of strings I will get. And this star, if I take non-zero, then I will get A, C plus B plus this type of strings I will get. Do you agree with me? Now notice something beautiful. All these strings can be generated by rule 4. Yes or no? AB plus all these strings can be generated by rule 4. Something more interesting. You can see all these strings can be generated by rule 2. Yes or no? You can see A, C plus B plus all these strings A, C plus B plus you can generate from rule 2 also. So basically, very interesting thing, you can see if there is any string and you are thinking for a moment, let's assume you are thinking that okay, for this string let's generate token 6. This is what you are thinking. Please understand, in your mind you are thinking that okay, for this string, let's assume for this string let's generate token 6. This is what you are thinking. But immediately what I will say that for this string, if you are generating token 6 because it is matching rule 6, so it is also matching either rule 2 or it is also matching rule 4. Yes or no? For this string, you want to generate token 6 because it is matching rule 6. Immediately I will say that because it is matching rule 6, so it is also matching rule 2 or rule 4, at least one of them. Yes or no? So because of priority, for this string, either you will use rule 2 or you will use rule 4. You will never use rule 6. You will never generate token 6. That's it. Okay, so you can see that I can also delete rule 6. Please tell me, did you understand? So you can notice here, because in this rule 6, any string that can be generated, that can also be generated by some rule above it. So here in this situation, I can say that rule 6 can be removed. I hope you understood this point. Is this clear to everyone? Tell me. So remember, this is also deleted. This can also be deleted. So which rules can never apply? The answer will be what? The answer will be rule 5, comma 6. Okay. Now let me give you the theorem also. You are waiting for the theorem. So final the theorem I am giving you. The theorem is like this. This is the explanation of the previous question. Now let me give you the theorem. You can see, if every string that matches rule y also matches some upper listed rule, then rule y can be removed as it will never be executed. Okay, so you can see this is the theorem. Remember, if you have a rule y, let's assume this is rule y. Okay, and these are the rules, some like this. Okay, like this. Now let me tell you, here every string that you can generate here, if that can be generated by some rule above it, then in this situation this rule will never be executed. Okay, so please understand that every string, if every string that possibly that matches, if every string that matches rule y also matches some upper listed rule, then rule y will never be used. So we can remove it. This is redundant. We can remove it. This is unnecessary. This is redundant. I hope you understood this point. Okay, very simple, right? Agree with me? So this is the note. And remember, what is the consequence of this note? There is a consequence of this note that we have already seen. This is the consequence of the previous note, that is, if rule y is subset of rule x, then immediately you can remove rule y. Okay, this is the consequence of the previous note. So that's it. This is the complete analysis of this type of question. Okay, this type of question is present in the Berkeley University also, Stanford University also, and I'm very sure in the future GATE exam, one day this type of question will come, because this is an interesting question. This is a simple question if you think about it. Yes or no? Some rules are given to you, and the question is asking which rule will never be used, will never be executed. This is not a complicated question. This is simple, common sense, logical question. I hope you understood the complete explanation. We have seen two type of question, one from Berkeley, another from Stanford, and we have done the complete analysis. We have seen the theorem, the result, the consequences, everything we have seen. I hope this has become crystal clear to everyone. Let's solve this Stanford question. In this question, some lexical specification, or I can say some lexical rules are given to us. These are the tokens, token 1 to 9, and these are the associated regular expressions. You can see here that this is the null character. In this particular lexer, in this particular lexical analyzer, for the null character also we generate a token. If you notice, I told you in the previous lecture, in the C language, in most of the languages, for the white spaces, for the new line character, sorry, this is the new line character, not null character. Okay, sorry, this is the new line character, not the null character. In this question, some lexical rules are given to us. These are the tokens, token 1 to token 9, and these are the associated regular expressions. Also notice one thing, this new line character. For this new line character also, in this lexical analyzer, we are generating a token, token 1. Remember, in the previous lecture, I told you that in the C language, in most of the programming languages, for the white spaces, like new line character, for them, we do not generate token. But in this particular lexical analyzer, for the new line character also, token is generated. Okay. So you can see these are the regular expressions, and corresponding to these regular expressions, these are the tokens generated. Now let me explain what is the question asking. You can see the question is asking that what will be the output of the following input. This is the input. Okay, you can see this. Remember, these are not multiple inputs. This is a single input. For this input, what will be the output? This is what the question is asking. Interesting question. This is a single input, multiple line input. It has multiple lines. For this input, what will be the output? This is what the question is asking. You can see what will be the output of the following input. Assume there is nothing to the right of last visible character on each line except a new line character. Means the visible character that you see, to the right of it there is a new line character, because you can easily notice there is a new line here, there is a new line here, new line here, new line here, and each line, the question is saying each line. So remember, for the last line also here there is a new line character. Basically, assume there is nothing to the right of last visible character on each line except a new line character. Okay, at the end of each line there is a new line character, and this is the input. Okay, so we need to find what will be the tokenization of this input. Very interesting question. I hope you understood the question. Now, first, before we solve this question, let me explain the meaning of some of these rules. Okay, this is very simple. Basically, here only A is there, capital A. This is also very simple, only small a is there. This is also very simple, only small d is there. Okay. Now let me tell you what is the meaning of this B to D star. Okay. Let me explain. This means B to D. Please understand. This means B to D. Okay. You can understand like this. This is basically B, C, D star. Is this clear? Okay. Because understand, this is not the curly braces. This is the bracket. Okay. So this basically means B to D. I hope you understood this point. Means B, C, D, whole star. Any sequence of B, C, D. Any sequence. Okay. This is very simple. This is ABC, only one string ABC. Okay. Next, you can see this A to C star, capital A to capital C star. This is basically same as capital A to capital C. Okay, is this clear? This is small a to small c whole star. This is same as basically three letters, small a, small b, small c whole star. Okay. Similarly, you can see here capital A to capital C whole plus. Then there is D. Then there is small a to small c whole plus. Okay, you can see plus means what? This means one or more, and star means zero or more. Okay, very simple. You already know this star means zero or more, and this plus this means one or more. Okay, I hope you understood the rules. Okay, once you understood the rules, now let's solve this question. This is a simple, beautiful question. First, what you do, this multiple line input, you convert into a single line. Okay, is this clear? Let's convert into a single line. So in the single line, it will be capital ABC. Then there is small d, small ABC. Then there is a new line character. Then there is capital A, then small ABCD. Then there is new line character. Then there is capital B, capital C. Then there is D, B, capital A. Then there is new line character. Then there is small b, small c. Then there is new line character. And after that, there is A, B, C, C, D, B, A. And remember, there is a new line character here also, because each line has a new line character. Okay, at the end, you can see to the right of each line, last visible character on each line. I hope you understood. So overall, this is the input. Okay, for this input, let's see what will be the tokenization. So let's read this. You can see we have capital A. Tell me, among these rules, you have first character, that is capital A. So among all these rules, which is in the race? Which regular expression, which rule is in the race? Capital A is there. Yes, this is in the race. This is out of race, out of race. This is small b to small d, out of race, out of race. This is out of race, yes or no? So you can easily see that when you see this capital A, then only this is in the race, this is in the race, also this is in the race. Okay. Now let's see the next character, that is capital AB. Now this is out of the race. Capital AB, this is in the race, this is in the race. Yes or no? This rule 7 and rule 9, they are in the race. When you see capital AB, because this is A to B, and here you have A to B whole plus, here you have A to C. This is A to C, this is A to C whole plus. Okay, so A to C means ABC. Let's read this ABC. Yes, this is in the race, this is in the race. Next you have, next there is D. Okay, yes or no? This is a capital A, capital B, capital C, small d. So tell me who is in the race now? Now this is not in the race because here you have capital A to capital C only. Means capital A, capital B, capital C. There is no small d here. So now only this is in the race. Okay, you can see after capital A, capital B, capital C, there is small d. Yes, there is small d. Then after that, small ABC. Yes, here you have small a to C. A to C means small a, small b, small c, whole plus. Okay, very interesting. So you can easily notice, and then there is a new line character. This new line character, if you see this total thing, now it is not matching. It is not matching any rule. So you go back to the last matching rule. Okay, the last match. So you can see this is the last match. Do you agree? This is matching with whom? What will be the output? Tell me. This output will be token 9 will be printed. Okay, yes or no? Is this clear? Very simple, right? Now, after that, there is a new line character. Please understand, in all these rules, you can notice the new line character is only in the first rule. The remaining do not have new line character. So for new line character, only this will be in the race. These will not be in the race. The remaining will not be in the race. So for the new line character, always this token 1 will be printed. Okay, so for the new line character, token 1 will be printed. After that, there is capital A, small a. Tell me who is in the race? Capital A, small a. These are not in the race. Capital A, small a. Who is in the race? Tell me. After capital A, there is a small a. No one is in the race. Yes or no? No one is in the race. So I can go back and I can only give for capital A. Is this clear? Because please understand, if you see this capital A, small a, after capital A, there is small a. So no rule is in the race. Okay. So what I can do, I can find the last match. So I can say this capital A, and who it is matching this capital A, this has higher priority. Actually, capital A is matching here also, here also. Okay, means I can print either 2 or I can print 7. Both are matching. Both are matching. So you can notice that this has higher priority because this is listed before rule 7. Rule 2 is listed before rule 7. So rule 2 has higher priority than rule 7. I told you in this order, the priority decreases. This has highest priority, this has lowest priority. So finally, I can say rule 2, token 2 will be generated. Very simple. Next, you have small a, small b, small c. So small ABC, this is in the race. This is also in the race. Yes or no? This is in the race. This is in the race. Notice this is not in the race because before small a, small b, small c, there must be d. There must be small d. Okay, because here you can see there must be d here. Okay, so I can say this is in the race. This is also in the race. Small a, small b, small c. After that, there is d. So you can notice now all are out of the race. If you focus on small a, b, c, d, then all are out of the race. So I can say that I will go back to the last match. Okay, the last match is small ABC. This small ABC, this is the last match. So for small ABC, this is also matching, this is also matching. So this has higher priority. So I will print token 6. Token 6 will be printed. Then there is D here. After that, there is new line character. Remember, I told you new line character is not part of any rule except the first rule. Okay, so for the new line character, always this token 1 will be generated. Okay, so what about this small d? This is a separate thing. For the small d, you can notice this rule 4, because this has higher priority. Actually, this is also matching. For small d, these two are matching. So we will print token 4. Okay, so token 4 will be printed. Understood so far? Then there is new line character. For the new line character, token 1 will be printed. Then capital BC, then small d. Capital BC, then small d. Here actually it is matching. See this last capital BC, then small d. So yes, this is matching because here you can see capital A to capital C. So it means ABC. And then there is a small d. Then there is small ABC. So you can see that capital BC, then small d, then small ABC. Yes, so far it is actually matching. Okay, yes or no? So for this, we will generate the token 9. Okay, next you have this A. You can see then there is new line character. For the new line character, we have to generate token 1. So for this A, what I will generate? For this capital A, the token 2 will be generated. Then for the new line, token 1 will be generated. Okay. After that, you can see small bc. What is matching? Small bc. This is not matching. Okay. You can see the rule 6. It is not matching because rule 6 will start with A. Small bc. This is matching. Small bc. Yes or no? This is matching because this is B to D, means BCD. Small bc. This is also matching. So for small b, small bc, this 5 we will print. Okay. Because this has high priority. So we will print token 5 for this small bc. Then for the new line character, the token 1 will be printed. Okay. Then there is small abccd. Small abcc. So who is matching? Small abc. Small abcc. So this is not matching. Small abcc, yes, this is matching. Okay, small abcc, this will match. So for small abcc till here, who is matching? Small abcc. This 8 I will print. Token 8 I will print. After that, there is small d ba. You can see small d, small db. This is matching small db. Yes or no? Notice small db. This is matching small db. Okay. You can see dba. Nothing else is matching. Okay. Because here there is a plus here. Please understand. Okay. There is a plus here. So we need capital. In this rule, in the rule number 9, there is a plus here, means it should start with either capital A or capital B or capital C. Then there should be, you can see somewhere there should be small d. Okay, so you can easily see that for this small db, this is small db, the token 5 will be printed. Okay, after that, there is a small a and new line. Okay, so now this is very easy. For the new line, token 1 will be generated, and for small a, token 3 will be generated. This is your output. That's it. I hope you understood. Is this clear? This was another variation. I hope you understood this. So I hope you understood everything that we have seen so far. In the next session, we are going to solve this GATE exam question. You can see this GATE CS 2018 question, lexical analyzer, these tokens, these corresponding regular expressions are there. This string is there. The question is asking what will be the tokenization, what will be the token stream. So this type of question we have already done. So you can take this GATE exam question as a homework. In the next session, we will do it. Okay. Let me give you one more homework from the University of Delaware. So please take this question also as a homework. And I would like you to pause the video and write your answer in the comments. Okay. So for this University of Delaware question, pause the video, try this question. The concept we have seen, similar type of questions we have done. And after solving this question, you write your answer, the token stream, the output, you write your answer in the comment. Okay. So I hope you understood everything in this lecture. In the next lecture, we will solve some more standard questions on lexical analyzer, some questions in which time complexity is also involved. These questions also we will do in the next session. We will also study what are lexical errors. In this lecture, we have seen one type of lexical error, that is tokenization fails. Okay, but there are some more lexical errors. So the complete list of lexical errors I will give you in the next session. And already we have seen in this lecture that lexical analyzer is basically a deterministic finite automata. This we have already seen in this lecture. Okay. So in the next lecture, our task will be some more standard questions on lexical analysis. Also this gate exam question. Also some questions, some standard questions in which time complexity is involved, and also lexical errors. Okay. So these topics, these questions we will solve in the next session. Okay. Thank you everyone. I hope you loved this session. Let me tell you, you can notice that this gate exam question came in 2018. Before 2018, this type of question from the lexical analysis never came. So before 2018, let me tell you, no student solved, no student did this type of questions. So when this question came in 2018, let me tell you, in 2018 my rank was all India rank 67. Okay, this was the first time I got top rank in the gate exam. This was my second attempt. In my first attempt in 2017, I got around 1200 rank. Okay, you can see. In this 2018 attempt, I got all India rank 67. This question I solved, but there were many students, many students who could not solve this simple question. Let me tell you the reason, because before 2018, there is no question from the lexical analyzer of this type of question. Okay, so when this question came in 2018 for the first time, many students were not able to solve it. And remember, this question, you can notice this is from the standard resources. Many this type of questions we have done. Similar type of questions we have done from Berkeley, from University of Delaware, from Stanford. A lot of similar type of questions we have already done. So remember, from the standard resources, questions come in the gate exam directly. Now many students will say, in this session we have done a lot of questions, yes or no, many different variety of questions, some variations which have never come in the gate exam. So some students, some people, what they will say, कि go classes में तो कुछ भी पढ़ा रहे हैं, standard university के question solve कर रहे हैं. In go classes they are solving standard university question. Okay, why are they solving standard university question? So let me just tell you, you can tell those people that standard university questions, the standard resources questions, they come in the gate exam directly. Okay, and it's just a matter of time. Maybe next year, or maybe in the future gate years, maybe all these questions that we have seen in this lecture, all the questions that we have done, all the variations that we have done, maybe they will come in the gate exam in the future. Okay, so it will benefit all the go classes students. One more thing, all the questions that we are solving, we are not by hearting anything. I am giving you the proper logic, the logical thinking. Okay, how to solve the question, the hint, the proof, the complete analysis. So all these things are basically very logical. From the concepts you can solve all these questions very easily. Okay, you don't need any new concept to solve these questions. The same basic concept just apply in these questions and you can get the answer. That's what we have done in this session, in every question, in each question. Okay, so thank you everyone. Please like this session, please put your feedback in the comments. Okay, thank you.